For centuries, humanity gazed at the stars, believing them to be eternal, unchanging lights in the cosmos. But hidden within the vastness of space, a new mystery was waiting to be uncovered. Pulsars. Spinning remnants of stars long gone, cosmic lighthouses that flash with unimaginable precision. Born in the fiery death throes of massive suns, these celestial beacons defy understanding, emitting radio pulses so regular they rival the precision of atomic clocks. But what are they? How did these stellar corpses become nature's most perfect timekeepers? And could they hold secrets that reshape our very understanding of the universe? It took the keen eyes of a young scientist, scanning endless radio signals, to recognize something no one had ever seen before. An unseen force, a pattern too perfect to be random. Some believed it was artificial, a message from another world. But the truth was even more astounding. These pulses, flashing from deep space, were the whispers of dead stars. Rotating at unfathomable speeds, pulsars revealed a universe far more violent, dynamic, and extreme than we had ever imagined. From supernovae to neutron stars, from gravitational waves to the very fabric of space-time, the study of pulsars has opened doors we never knew existed. Prepare for a journey into the heart of stellar death, where the end of a star marks the beginning of one of the universe's greatest mysteries. This is the story of pulsars, the ticking clocks of the cosmos. Comprehending pulsars necessitates an understanding of stellar phenomena. Pulsars arise from the remnants of stars that have experienced catastrophic explosions termed supernovae, signifying their demise. Before our discussion, it is crucial to understand the principles of stellar luminosity, their energy sources, their lifespan, and the factors contributing to their finite existence. At the core of our discussion is the investigation into why only the most massive stars produce pulsars, and exclusively at the point of their death. The Sun's diameter is 100 times greater than Earth's, a massive sphere of plasma that has produced and will persist in producing immense quantities of energy for billions of years. Notwithstanding its considerable dimensions, we categorize the Sun as a diminutive star. The Sun will never become a pulsar due to its insufficient mass. The formation of a pulsar requires a massive star considerably larger than the Sun. It is now understood that stars are substantial spheres, predominantly composed of gas, specifically hydrogen and helium. Gravity maintains the spherical configuration of a star's gaseous composition, while exerting pressure to compress it into a more confined volume. This compresses the material at the core of the star. The substantial heat and pressure induce the fusion of lighter element atoms, resulting in the formation of heavier elements and the release of energy. The release of that energy inhibits the star from fully collapsing. The star will remain inflated against gravitational forces if it has adequate fuel. However, the star will undergo implosion and cease to exist upon the depletion of its fuel, as is inevitable. This signifies the ultimate fate of all stars. Consequently, although stars may seem eternal, this is merely an illusion. We introduce them, permit their existence, and subsequently observe their disappearance. What constitutes the basis of our comprehension? Take the sun, for instance. Humanity will not be present to witness the sun's extinction. The diurnal sky showcases a transient depiction of a middle-aged star. The sun has undergone minimal alteration throughout human history. We regard it as youthful. Nonetheless, alternative approaches are available for revealing the sun's historical and future trajectories. Studying celestial bodies indicates that stars resemble other suns, enabling us to infer the sun's origin and probable extinction by examining stars at various phases of their life cycles. It is akin to being among a diverse assembly of individuals ranging from 1 to 100. By observing individuals around us, we can deduce that their experiences will mirror our own. We have employed a comparable methodology to comprehend stars. However, a considerable challenge arises in studying stars. Their vast distances make them physically unreachable. All scientific fields depend on experimentation to evaluate hypotheses. Any experiment aims to manipulate a variable and examine the resulting changes. Astrophysicists cannot achieve this. The stars are excessively distant and immense in size and energy for us to exert influence. The solution is to permit nature to perform her own boundless experiments and to discern patterns in the gathered outcomes. Astronomical observation depends on and frequently drives the development of new instruments. Recent discoveries have depended on and advanced the development of larger, more sophisticated telescopes and the sensitivity and diversity of instruments that capture light from distant stars. The most notable advancement in astronomical instrumentation following the invention of the telescope transpired in the early 19th century with the advent of spectroscopy. Spectroscopy depends on dispersion, which separates light into its constituent colors. A rainbow illustrates natural dispersion. Newton investigated dispersion 150 years before the emergence of spectroscopy. In his famous experiment, Newton allowed sunlight to pass through a small opening in a window shutter and a glass prism. He witnessed a remarkable array of colors emanating with the intensity of the original sunlight. Nonetheless, Newton progressed the experiment further. He permitted the colored light to traverse a second prism, thus reconstituting white light. White light is not a singular entity, but a composite of all the rainbow colors. Newton neglected a series of dark lines in the spectrum, resembling precisely removed narrow light segments. In 1702, British physicist William Hyde Wollaston observed the lines, while the distinguished German optician, Joseph von Fraunhofer, performed the first thorough analysis of them. Fraunhofer utilized his sophisticated instruments to map numerous dark lines, now referred to as Fraunhofer lines, and applied this technique to observe the moon and planets. He noted that the arrangement of lines in planetary spectra was consistently analogous to that of the suns, which they reflected. Upon analyzing the stellar spectra, he discovered that the configuration of lines in the star spectra markedly differed from that of the sun's spectrum. This functioned as a stellar equivalent of a barcode, providing detailed information about the identity and composition of the stars. Nonetheless, Fraunhofer was an optician, not a physicist, and he died oblivious to the importance of his findings. The identification of spectral lines led astronomers to contemplate the classification of stars. This began with the endeavors of American amateur astronomer Lewis M. Rutherford and Italian Jesuit Angelo Secchi. A cohort of women, supervised by astronomer Edward Charles Pickering at Harvard College Observatory, categorized stars according to the configuration of spectral lines. Restricted from enrolling in courses at their employing university, over 10 women examined the spectra of thousands of stars and initiated their classification. At this juncture, we observed the spectral lines produced by different elements. He initially categorized the stars according to the intensity of the hydrogen-induced spectral lines, assigning each a letter designation such as A, B, C, etc. An analyst, Annie Jump Cannon, noted a gradual change in the spectra's appearance and restructured the sequence. The consequence is the disorganized notation OBAFGKMRN, which remains the subject of examination by professional and amateur astronomers. This was pure taxonomy. No one comprehended the importance of the classifications. The spectral lines distinctly indicated a characteristic of the stars, potentially signifying a relationship. A physical explanation was essential to comprehend that relationship. The solution emerged from the endeavors of multiple scientists, ultimately unifying two previously distinct disciplines, astronomy and nuclear physics. We hypothesized that the chemical composition of different substances, as evidenced by Fraunhofer's lines, would likewise apply to the stars. This is accurate. However, the concept became progressively insufficient as star surveys expanded. In the early 1900s, two astronomers independently established a crucial link that enabled a true understanding of stellar evolution. Henry Norris Russell, associated with Princeton, and Einar Hertzsprung, a Danish chemical engineer turned astronomer, analyzed the stellar spectra in two notable clusters, the Hyades and Pleiades. Visible to the naked eye in the early evening skies of December, these vast clusters of stars are physically connected in space and are situated at an equal distance from Earth. A star's apparent luminosity in the night sky is contingent upon its intrinsic brightness and distance from the observer. Since the stars in the Pleiades and Hyades clusters are equidistant, any variations in their apparent brightness must originate from the stars themselves. Astronomers knew how to determine the distances to stars utilizing the parallax method. This phenomenon is evident to anyone who has witnessed the relative motion of proximate and distant objects from a moving vehicle. Proximate objects move considerably more against the distant background. The same phenomenon can be observed among the stars. As Earth traverses its orbit, the proximate stars shift position relative to the more distant stellar backdrop. Meticulous measurement of this relative positional variation enables astronomers to ascertain the distances to proximate stars. By examining the apparent luminosity of stars and their distances through parallax, we can ascertain their intrinsic brightness and various other physical attributes, including their energy output. The Pleiades and Hyades clusters comprise stars at comparable distances, facilitating a direct comparison of their energy output or intrinsic luminosity. Hertzsprung and Russell identified a direct correlation between the variations in line widths of stellar spectra and the luminosities of stars through meticulous observation and analysis. Associated stars in space imply a common origin from the same primordial material, signifying a shared composition. This suggested that differences in chemical composition alone could not explain the discrepancies in the spectra of stars within the same cluster. Astronomers had by this stage ascertained the temperatures of stars through the analysis of their colors, akin to a metal in a furnace emitting different hues as it heats. The colors of stars signify their surface temperature. The luminosity of a star is not exclusively dictated by its temperature. Cool stars can exceed hotter stars in brightness, simply due to their greater size. For stars exhibiting fluctuating brightness, yet identical temperature, luminosity must be contingent upon physical size. Astronomers could ascertain the distances to stars through spectroscopy rather than parallax for the first time. They achieved this by analyzing a star's brightness, intrinsic luminosity, determined from the widths of the spectral lines, and temperature, inferred from its color. Russell and Hertzsprung constructed a simple chart by plotting the star's spectral type color temperature against their luminosity, resulting in smooth curves formed by the plotted stars. A superficial analysis of the Hertzsprung-Russell HR diagram reveals a notable correlation among the stars. Most stars are predominantly located along a band that stretches from the upper left corner, luminous and hot, to the lower right, faint and cool, known as the main sequence. Their star groupings included luminous, cool stars in the upper right, and faint, hot stars scattered along the bottom. As astronomers charted additional stars, the curves increasingly reflected the evolutionary changes of the stars. Revisiting our analogy of analyzing a crowd to infer an individual human life cycle, it resembles plotting two characteristics of humans, such as height and wrinkles, and noting that only tall individuals display wrinkles, albeit not all tall individuals do. A relationship exists. Astronomers asserted that the Hertzsprung-Russell diagram depicted an evolutionary correlation. Hertzsprung and Russell elucidated the relationship. Both were entirely erroneous. The elucidation would become apparent once astronomers comprehended the processes within the star's interiors. Stars are colossal, generating substantial energy over extended periods. Nonetheless, from where did all the energy originate? In the early years of the 20th century, Arthur Schuster and Carl Schwarzschild formulated a model of the Sun, distinguished by escalating temperature and density with depth. This demonstrated that the external emission of radiation could offset the internal gravitational pull. Arthur Eddington originated, expanded upon, and articulated his stellar structure theory in his seminal publication, The Internal Constitution of the Stars. Eddington integrated time into his computations and evidenced that the stars on the Hertzsprung-Russell diagram represented an evolutionary transition from one classification to another. The notable aspect was the duration of evolution, measured not in millions of years, but in billions of years. What maintains the luminosity of the Sun and other stars over extended durations? The solution emerged from two innovative scientific concepts: atomic physics and the theory of relativity. A new scientific discipline was emerging at the century's turn that would clarify the age of the Earth and Sun and the energy of the stars. Consequently, gravitational collapse constituted the sole source of stellar energy. Marie and Pierre Curie discovered that radioactive decay can convert specific elements into lighter elements. Uranium progressively undergoes decay into the lighter, more stable element lead, converting a fraction of the original atom's mass into energy. This event is termed nuclear fission. Eddington's investigation of stellar nature led to the recognition of radioactivity as a viable energy source. It was once suggested that the Sun could harness energy from radium decay, measured at merely 3.6 grams per cubic meter, for its own power generation. Despite straying from the primary subject, the discussion still included alternative energy sources, the acknowledgement that the fission of heavy elements and the fusion of lighter elements into heavier ones produces considerable energy represented a major advancement. The stellar spectra indicated the existence of hydrogen and helium. Research indicates that the mass of the helium nucleus is approximately 0.5% lower than the mass of the 4 hydrogen nuclei that comprise it. Can hydrogen fusion with helium produce sufficient energy to sustain a star? Einstein's famous equation E equals mc squared states that matter is indestructible, but can be converted into energy. Notwithstanding the negligible mass disparity between hydrogen and helium atoms, when multiplied by the square of the speed of light, even a 0.5% variation yields a significant quantity of energy. The objective was to accomplish the fusion of hydrogen nuclei. Eddington estimated the Sun's internal temperature to be around 40 million degrees. Is this temperature adequate to enable nuclear fusion? A hydrogen atom comprises a positively charged proton and an electron. Protons and electrons form a plasma state at elevated temperatures, facilitating unrestricted interactions among protons. The amalgamation of two positively charged protons must surmount the Coulomb barrier, similar to the repulsion experienced between like charges. The solution resided in the understanding that the electrostatic force separating individual protons is not their sole interaction. The fundamental forces regulate the universe. Electromagnetism segregates protons. Gravitation. The nuclear force is feeble. A robust nuclear force exists in our universe. The ultimate force, considerably more powerful than electromagnetism, holds protons together within atomic nuclei. Nonetheless, it functions efficiently only within a restricted range, beyond which electromagnetism dominates. In 1929, the Russian-born American physicist George Gamow clarified the technique to position protons closely enough for a strong nuclear force to dominate. He developed a technique termed quantum tunneling, an alternative pathway to the atomic nucleus. It enabled the fusion of protons to form newer, heavier elements, releasing energy. This type of fusion does not transpire at ambient temperature. While seated on a chair, the electrons in your atoms repel those in the chair, obstructing any fusion or penetration. However, the exceptional temperatures and pressures within a massive entity like a star create a distinct scenario. Atoms are accelerating at elevated velocities due to the increased temperature. Collisions occur, producing adequate energy to overcome electrostatic repulsion, forming new, heavier particles and elements. Although infrequent, the vast quantity of atoms in a star guarantees that, despite the low probability, sufficient collisions transpire to sustain the star's energy production. Furthermore, owing to the colossal dimensions of stars, the energy discharge would endure for an extensive period, measured in millions of years. We have conclusively confirmed Eddington's claim that atomic energy is the fundamental source of stars. The fusion of elements in stars profoundly influences us, as we share the same elements. Researchers Fred Hoyle, William Fowler, Geoffrey Burbidge, and E.E. In the late 1950s, Margaret Burbidge clarified how stars transform simple elements into heavier ones, known as nucleosynthesis. Elements with fewer protons are more easily fused due to diminished repulsive forces that must be surmounted. The smallest element is hydrogen, which has only one nuclear charge and mass. This accomplishment necessitates exceptionally high temperatures. Hydrogen must experience fusion at approximately 15 million Kelvin. The amalgamation of hydrogen nuclei produces helium with a nuclear mass of 4. Helium's higher density causes it to sink to the star's core, hydrogen layer above, akin to the egg white surrounding the yolk. Hydrogen fusion persists in a shell encasing the helium core, maintaining the star's luminosity at previous levels. The subsequent events are dictated by the star's initial mass, and, as will be demonstrated, the destinies of stars with varying masses diverge markedly. The temperature and pressure in the newly formed helium core of the Sun increase until helium fusion commences at 100 million Kelvin, resulting in the production of carbon. The denser carbon sinks below the helium towards the star's core, where pressure and temperature continuously increase. At this juncture, the Sun's external visage will undergo significant transformation. The Sun's mass expands and cools, growing to over 90 times its main sequence size, and engulfing the planets Mercury and Venus. As the Sun expands, its luminosity increases. However, the cooling of its outer atmosphere produces a reddish hue, indicating its evolution into a red giant. The HR diagram shifts from the main sequence to the upper right quadrant. Simultaneously, the star's intense, dense core endures in the depths. A star with fewer than 8 solar masses will undergo evolution into a red giant. The continuous emission of subatomic particles called neutrinos cools these stars, hindering their capacity to attain the temperatures necessary for carbon-oxygen fusion. These unusual particles traverse from the core outward through the star without engaging with energetic matter. Fragile hydrogen and helium layers encase the carbon and oxygen-dominant core. Stars, ranging from 8 to 10 solar masses, have sufficient mass to generate the temperatures and pressures necessary to convert carbon into oxygen, neon, and magnesium. Following a period dependent on its initial mass, the star takes on an onion-like structure, displaying concentric layers of increasingly dense elements, from the outermost hydrogen to helium, carbon, and finally, the core. Nevertheless, supplementary measures are necessary to prolong the star's longevity. Ultimately, it depletes its nuclear fuel. The radiation pressure from the core progressively ejects the gas shell over a century. His gently illuminated shell transforms into a planetary nebula, revealing the core at its center, now designated as a white dwarf star, a slowly cooling remnant approximately the size of Earth. From an external viewpoint, the star appears to increase in temperature. However, due to its diminutive size compared to main sequence stars, its luminosity decreases. On the HR diagram, the star moves from the red giant region in the upper right to a position lower and to the left. The trajectory moves through the main sequence and culminates in the lower left of the HR diagram, persisting for billions of years as it slowly cools and fades from the stellar realm. The fate of massive stars is more consequential in the context of pulsars. Should a star's initial mass surpass 10 solar masses, it can generate sufficient pressure and temperature to facilitate the fusion of increasingly heavier elements. This emits a substantially greater quantity of light into space than lower-mass stars, and it does so at a markedly faster rate. The star's increased mass generates heightened gravitational pressure at its core, accelerating the nucleosynthesis rate. A star with a solar mass has an approximate lifespan of 8 billion years, whereas a massive star lasts around 100 million years. Massive stars incessantly synthesize heavier elements throughout their brief lifespans, accumulating them sequentially in their cores. The denser elements sink to the core, while successive layers of less dense elements envelop it, akin layers of an onion. The accumulation of iron in the core results in its failure. The amalgamation of iron nuclei necessitates energy rather than generating it. To date, the amalgamation of lighter elements with heavier counterparts has functioned as an energy source for the star, sustaining its expansion against the unyielding force of gravity. Nonetheless, gravity, the universe's weakest yet most pervasive force, ultimately triumphs. The star cannot sustain its expansion against gravitational collapse after depleting its nuclear fuel. The nuclear fusion processes that supported its transient existence have now ceased. Most of the star's outer layers briefly implode, accelerating towards the core. Here they collide in a colossal impact so intense that they instantaneously generate elements denser than iron that form our known worlds. A notable implosion results in a core rebound. The aggregation of matter encircling the core during the collapse releases considerable energy. The star explosively discharges, scattering the newly formed elements in every direction. The eruption emits light equivalent to that of 100 billion stars. It has evolved into a supernova. For a brief duration, it exceeds the entirety of the galaxy. As the star's outer layers extend into space, the stellar core undergoes collapse. Without radiation pressure, gravity prevails and compresses the core to remarkable densities. An unusual object arises from the death of a massive star. It radiates a luminous glow and spins at an exceptional speed, exhibiting such density that it warps space-time and emits powerful beams of radio waves into the cosmos. In January 1932, the couple, Frederick and Irene Joliot-Curie, published a paper in the Comptes Rendus Journal of the French Academy of Sciences, which was reviewed by the young British researcher James Chadwick. The paper examined the interaction of alpha particles emitted from a polonium sample with a fragment of the toxic metal beryllium. The experiment produced a highly energetic yet intangible form of radiation. Although they could not directly measure the radiation, they could detect protons emitted from various materials placed in the radiation's path. They were bewildered that this novel radiation type permeated nearly all materials more easily than any previously observed form. Prior experiments executed by Walter Bother and his pupil Herbert Becker in Germany revealed that the radiation could permeate 200 millimeters of lead. This is noteworthy, given that less than 1 millimeter of lead is required to impede the most potent energy known at that time, gamma rays. The intensity of this novel radiation made its nuclear origin challenging to contest. Both teams hypothesized that the unidentified radiation was a more energetic form of gamma rays. If it could displace electrons from metals, why could it not also eject protons from the nuclei of other materials? Nonetheless, this represented only a portion of the narrative. Chadwick was cognizant of the remainder. He was cognizant of their findings, yet he had not recognized them. Driven by urgency, he reiterated and elaborated on the experiments, demonstrating the existence of the neutron, the atom's third component, within 3 weeks of comprehensive research. The discovery could profoundly influence both cosmic and terrestrial occurrence. James Chadwick was born in Manchester, England, on October 20th, 1891. Upon graduating from the Honours School of Physics in 1911, he devoted 2 years to working under New Zealander Ernest Rutherford at the Physical Laboratory of Manchester University. Faced with financial challenges, Chadwick moved to Berlin to study at the Physikalische Technische Reichsanstalt in Charlottenburg under Professor Hans Geiger, who was recognized for the Geiger counter. In the subsequent year, hostilities ensued. Thomas Cook, the travel company, notified British citizens that they were not under any immediate threat and therefore did not need to evacuate Germany. However, Chadwick was subsequently captured as a civilian prisoner of war in the deserted stables of a racetrack at Zivilgefangenenlager, Ruhleben, where he remained for the next 4 years. He was forbidden from conducting experiments but allowed to read and participate in discussions with other physicists. Chadwick conducted minimal research despite the adverse conditions, utilizing a toothpaste extensively promoted by Berlin Auer during that period. The toothpaste included thorium to improve tooth brightness. Employ toothpaste that incorporates thorium. Exhibit radiant, luminous teeth, an exceptional brilliance. Following the war's conclusion, Chadwick returned to Manchester, rejoining Rutherford in transmuting elements, transforming one element into another. Alchemists sought to accomplish this objective for numerous centuries, but were entirely unsuccessful. Eddington posited that stars could accomplish what alchemists could not. Subsequently, Rutherford aimed to comprehend the underlying mechanism. After the 19th century, Rutherford performed experiments that evidenced the existence of the atom's nucleus. Although most particles traversed the gold foil directly, he illustrated that some was deflected backward. Rutherford famously remarked that as if one discharged a 15-inch naval shell at a sheet of tissue paper, only for the shell to rebound and strike you. This experiment prompted Rutherford to deduce that the atom primarily consists of a nebulous cloud of electrons orbiting a small, dense, impenetrable nucleus. What is the status of the nucleus? What materials constituted it? During that period, scientists identified 2 particles, the positively charged proton and the negatively charged electron, with the proton possessing greater mass. The problem was that the masses of different elements were incongruent. A hydrogen nucleus possesses a charge of +1 and a mass equivalent to a proton. In contrast, a helium nucleus carries a +2 charge with a mass 4 times greater than a hydrogen nucleus. 4 protons in the nucleus and 2 electrons were necessary to neutralize the electrical charge, culminating in this mass. Despite possessing mass, scientists regard electrons silently light compared to protons, rendering their contribution to overall mass. negligible for the issues examined. However, this model displayed one further problem. In 1925, Dutch scientists George Uhlenbeck and Samuel Goudsmit identified a fundamental characteristic of nuclei, protons and electrons termed spin, whereby each particle exhibits a spin of either +1/2 or -1/2, with no intermediate values. The aggregate of the particle spins of an odd number of particles will produce a half-integer outcome such as 1.5 or 3.5. Upon measuring the total spin of a nitrogen nucleus, we determined it to be an integer despite consisting of 21 particles, 14 protons and 7 electrons, which neutralize the positive charge of the 7 protons by Rutherford's theory. A third type of particle must exist within the atom that does not influence its charge but contributes to its mass equivalent to that of a proton. Rutherford posited that this substantial neutral particle must amalgamate the dense proton with the lightweight electron, elucidating the observed nuclei masses. In his Bakerian lecture to the Royal Society in 1920, Rutherford clarified that it may be possible for an electron to associate more closely with the hydrogen nucleus, resulting in a form of neutral doublet. Rutherford named this theoretical particle the neutron. Rutherford and his students devoted the subsequent 12 years to pursuing the neutron but have not yet achieved success. In 1964, Chadwick noted that some efforts were so desperate, so far-fetched, as to belong to the days of alchemy. Nevertheless, after reviewing the Joliot-Curie paper, he recognized he was close to uncovering this elusive particle. The Joliot-Curies posited that the penetrating radiation consisted of gamma rays. Chadwick rejected this explanation, asserting that gamma rays lacked sufficient energy to produce the observed outcomes, as they could not dislodge protons from the tested materials at the recorded velocities. Chadwick had already succeeded by the time the Joliot-Curies reassessed their stance 3 weeks post-publication of their findings. Chadwick designated a restricted time frame to replicate the Joliot-Curie experiment. Chadwick continued working late into the night, ignoring Rutherford's directive against laboratory work after 6 p.m., as he was unwilling to waste time or endanger his delicate experimental apparatus due to possible interruptions from other researchers. Chadwick employed polonium as a source of alpha particles. He placed a beryllium sample before it, from which enigmatic, penetrating rays emanated. He arranged various targets along the path of these rays: hydrogen, helium, lithium, beryllium, carbon, air, and argon. Chadwick subsequently placed a detector before the samples to detect any emitted particles. The unidentified radiation displaced protons from the samples, which he later detected. Chadwick demonstrated that gamma rays did not possess adequate energy to displace particles from the samples by measuring their velocity. The penetrating radiation necessitated particles with a mass comparable to a proton, yet devoid of any electrical charge. In a letter to the journal, Nature dated February 27, 1932, he asserted, "The difficulties dissipate, however, if one posits that the radiation consists of particles with a mass of 1 and a charge of 0, or neutrons." Exhausted yet revitalized, Chadwick announced his discovery at a relaxed gathering of physicists known as the Kapitsa Club. The participants reacted with great enthusiasm and acknowledged the significance of the discovery. In a comprehensive report of his experiment published in the Proceedings of the Royal Society, Chadwick expressed caution regarding his findings. "It is evident that we must either abandon the principle of conservation of energy and momentum in these collisions, or formulate an alternative theory concerning the nature of the radiation. The law of energy conservation, that energy cannot be created or annihilated, is broadly acknowledged. In 1932, a debate persisted concerning the applicability of identical conservation laws in both quantum and macroscopic domains. Chadwick stated, "All issues related to collisions are resolved if we posit that the radiation is not quantum, but consists of particles with a mass nearly equivalent to that of the proton. This encompasses challenges regarding their frequency and energy transfer among varying masses." We must also presume that the particle possesses no net charge to comprehend the extent of radiation penetration. The particle may signify a close fusion of a proton and an electron, similar to the neutron discussed by Rutherford in his 1920 Bakerian lecture. What is the current status of the Joliot-Curies? Frederick was understandably disheartened by being usurped by Chadwick, and privately conveyed his frustration about the requirement to publish scientific evidence to establish precedents, while witnessing other researchers exploit that published work. This served as the impetus for Chadwick's success. Nonetheless, a magnanimous Frederick publicly recognized Chadwick for the discovery. Electrically neutral neutrons are completely unaffected by the positive repulsive force generated by protons in an atomic nucleus. Consequently, they possess a remarkable capacity to infiltrate the nuclei of other atoms. In early 1939, while conducting research in Berlin, Otto Hahn demonstrated that the uranium nucleus undergoes fission when exposed to neutron bombardment, releasing significant energy. 2 months later, the Joliot-Curies published a letter in Nature, asserting that the uranium nucleus experienced fission and emitted supplementary neutrons, which could infiltrate and further divide additional uranium nuclei, consequently releasing even greater energy. Some viewed the onset of a chain reaction as exhilarating, while others considered the consequences alarming. Physicists from both factions acknowledged that the Joliot-Curie discoveries suggested releasing substantial energy with dire implications for weaponry technology. They had laid the foundation for the world's inaugural atomic bomb. Years later, they would utilize the same scientific principles that had revealed the nature of the stars to annihilate hundreds of thousands of lives and expose the rest of humanity to an ongoing threat of extinction. During this time, an extraordinary young Indian scientist traveled from India to England to study under Eddington. Subramanian Chandrasekhar was an eminent scholar who obtained a scholarship from the Indian government to continue his education in England. Throughout the journey, he had ample opportunity for reflection. He was adept in German, had examined Einstein's papers on relativity theory, and understood the extreme conditions present within stars. The extreme conditions of stars that have exhausted their nuclear fuel perplexed him. What transpired subsequently? Following the life cycle of our Sun, the nuclear reactions that have sustained it for over 8 billion years will terminate. Gravity will dominate. The weakest of the 4 fundamental forces in the universe is also persistently patient. Despite the significant challenge posed by nuclear fusion, the conflict has ended. As the star's outer layers gradually disperse into space, gravity pulls the remnants of the star's core inward. Ultimately, the star halts its contraction and evolves into a white dwarf. In Chandrasekhar's era, white dwarf stars surpassed theoretical frameworks. Nearly a century prior, Friedrich Wilhelm Bessel, the director of the Königsberg Observatory, noted the unusual oscillation of the brightest star in the sky. He suggested that the star Sirius demonstrated lateral oscillation while orbiting a common center of gravity with an invisible companion. Despite the dismissal of his proposal, American optician Alvin George Clark discerned the elusive star that Bessel had predicted 18 years earlier. In 1914, American astronomer Walter Sidney Adams successfully captured the spectrum of this atypical star and established that it was as hot as its companion, Sirius. The star's diminutive size is the sole rationale for its elevated temperature and unexpectedly low luminosity. Rutherford's research elucidated atomic structure, revealing that atoms predominantly consist of empty space, with a minuscule nucleus enveloped by a cloud of electrons. This comprehension facilitated the conceptualization of matter as fragmented and compressed to the degree that an entire sun could be diminished to the dimensions of planet Earth. After its life cycle, a star's core collapses, expelling electrons from atomic nuclei and forming a nucleus-electron composite known as degenerate matter. However, no electron can occupy the same quantum state, as another electron, a phenomenon known as the Pauli exclusion principle. The core attains a state in which the electrons oppose additional compression. It is akin to attempting to compress a bag of billiard balls. Once they are in contact, further diminution of the bag's size is unfeasible. The star, with a diameter similar to Earth's, halts its core contraction and exists between existence and annihilation. Although white dwarfs exhibit exceptional luminosity at their surface, especially in their early stages, they appear remarkably dim in the sky due to their diminutive size. Without nuclear reactions to maintain its temperature, the initially hot white dwarf progressively loses its residual heat to space. Over billions of years, it evolves from white to yellow, red, and black. As small as a diminutive star and as dark as the profound abyss, any residual planets will persist in orbiting the concealed stellar remnant in total obscurity. Consistently. Chandrasekhar's investigation focused not on how a star could achieve such diminutive dimensions, but on what inhibits it from further contraction, and what transpires at such densities. Chandrasekhar increasingly acknowledged the existence of a maximum mass for a white dwarf. Note that we employ the term massive, not large. Greater mass leads to diminished white dwarf dimensions, which is paradoxical. Augmenting the mass of a white dwarf would consequently intensify gravitational forces, further compressing the stellar remnant. Chandrasekhar demonstrated his brilliance by calculating, using only pen and paper, that a white dwarf experiences further catastrophic collapse beyond a mass of approximately 1.44 solar masses. Gravity exceeds the repulsive force of electrons. Chandrasekhar was bewildered by the question concerning the nature of the white dwarf's collapse. Upon his arrival in England, he was ready to confront this issue. Nevertheless, Eddington's and other British scientists' reactions to his theory could have been more positive. Eddington would categorically reject Chandrasekhar's conclusions. Chandrasekhar introduced his theory in January 1935 at a meeting of the Royal Astronomical Society. Following his lecture, Eddington repudiated the entire concept. In one of the most illustrious controversies in scientific history, Eddington categorically dismissed Chandrasekhar's findings with remarkable severity. He asserted to the audience that a natural law ought to exist to prevent a star from displaying such absurd behavior. No one contested the legendary figure. Eddington's esteemed reputation hindered research on the properties of small, dense stars for an extended period. Chandrasekhar, approaching the forecast of neutron stars, perceived that Eddington's critique had compromised his chances for tenure at a British university, leading to his migration to the United States, where he joined the faculty of the University of Chicago. He stayed there for the next 58 years of his scientific career, establishing himself as one of the foremost astronomers of the 20th century. The hypothesis concerning stellar collapse persisted beyond that juncture. That year, the young physicist Lev Davidovich Landau returned to Russia to take on two roles: head of the theory division at the Ukrainian Technical Institute in Kharkiv, and chair of theoretical physics at the Kharkiv Institute of Mechanical Engineering. Landau was a mathematical prodigy, completing his secondary education at 13. He began his mathematics, physics, and chemistry studies at Baku University, later known as Kirov Azerbaijan State University, the following year, and transferred to Leningrad State University 2 years later, graduating in 1927. In 1934, Landau earned his doctorate in physical and mathematical sciences in Kharkiv. Landau's research spanned a range of extreme physics, including atomic collisions, astrophysics, low-temperature physics, and quantum field theory. His crucial contribution clarified liquid helium's unusual behavior at cryogenic temperatures. Helium transitions into a superfluid, a peculiar state of matter that exhibits resistance-free flow at just a few degrees above absolute zero. The superfluid demonstrates unusual behaviors, such as rising into or descending from a beaker, until the helium level outside matches that inside the beaker. Landau developed a theory to clarify the superfluidity of helium, earning him the Nobel Prize in Physics in 1962. In later years, Landau was imprisoned by the Stalinist regime for purported espionage on behalf of Germany. The prison conditions were so harsh that after 1 year, he doubted his survival for more than another 6 months. Russian and international academics, including notable individuals like Peter Kapitsa and Niels Bohr, appealed to Stalin for Landau's release. Kapitsa unequivocally threatened to terminate all research in protest of the incarceration. Landau was released from imprisonment in 1939 and designated as a research fellow at the Institute of Physical Problems. Before Hadwick discovering the neutron, Landau formulated his hypothesis concerning a star that had collapsed to an exceptional density as a due gravitational force. Before, and independently of Chandrasekhar, Landau established an upper mass limit for a white dwarf, approximately 1.5 solar masses. Unaware of the contributions of Chadwick or Chandrasekhar, Landau conceptualized a star that achieved the density of an atomic nucleus, subsequently labeling it a nucleus star. He examined its characteristics and determined that it possessed a maximum mass. He subsequently determined that it could not exist, as the concept of such a collapse contradicted the notion of stars possessing solar masses. Although Landau's nucleus stars were not neutron stars as currently defined, he was the inaugural predictor of such dense stellar objects, and, surprisingly, his forecast has remained largely overlooked in the ensuing decades. American astronomers Fritz Zwicky and Walter Baade formulated the first widely acknowledged prediction of ultra-dense stars. Baade was a crucial observational astronomer of the 20th century. He was born in Germany and worked at Hamburg Observatory from 1919 to 1931, after which he moved to the United States to join Mount Wilson Observatory. In 1917, Mount Wilson contained the world's largest astronomical apparatus, the 2.5-meter Hooker telescope. Los Angeles and the San Gabriel Valley encountered partial blackouts during the war years. While most Mount Wilson observers focused on weapons development, Baade, designated as an enemy alien, remained restricted to Los Angeles. Commencing in April 1942, all enemy aliens were imposed a military curfew from 8 p.m. to 6 a.m. Nevertheless, the director of the observatory, Walter Adams, appealed to the government and obtained special permission for Baade to remain outdoors after dark, provided he justified it with professional obligations. He was among the world's most adept observers, almost isolated at the largest telescope beneath obscured skies. Baade employed time efficiently and made a paramount contribution. He aimed the 2.5-meter Hooker telescope at the Andromeda Galaxy, M31, and its companion galaxies, M32 and NGC 205. Baade effectively identified red giant stars utilizing newly acquired photographic plates attuned to the red spectrum. However, upon examining the developed plates, Baade observed a conspicuous absence of red and blue supergiant stars, which are prevalent in the spiral arms of the Milky Way. The most luminous stars were yellow giants. Baade classified two categories of stars within the galaxy: population 1 stars, which are youthful and metal-enriched, encompassing the radiant red and blue supergiants. They primarily inhabit the spiral arms of the galaxy. Population 2 stars are primarily situated near the galactic core or within the halo and comprise the majority of stars in elliptical galaxies. We have established that population 2 stars are primordial and deficient in metals, constituting a galaxy's earliest generation of stars. Baade's discovery had profound implications and laid the groundwork for subsequent galaxy and stellar evolution research. Zwicky was an outstanding scientist who contributed substantially to astronomy and various other disciplines. Zwicky, a Bulgarian native of Swiss descent, dedicated most of his professional career to the United States. After earning a PhD in physics in 1922 from the Swiss Federal Institute of Technology in Zurich, he moved to the United States, serving as a faculty member at the California Institute of Technology in 1922 Pasadena from 1925 to 1972. Zwicky's contributions encompassed the prediction of dark matter distribution in the universe via gravitational lensing and the development of some of the earliest jet engines. A select few scientists possess intellects significantly advanced for their era. Fritz Zwicky was undoubtedly a prominent example of this phenomenon. Zwicky was an exuberant individual with a distinct accent. Even after nearly 50 years of living in the United States, he was flamboyant and self-centered, harboring a contemptuous attitude towards many colleagues. One of his favored insults was designating individuals he disdained as spherical bastards. He elucidated that they were despicable irrespective of the angle from which one observed them. Zwicky was predominantly an observational astronomer. Although he participated in considerable theoretical endeavors, he is best known for his observational achievements. He was one of the first to establish that the observed concentrations of galaxies, initially identified by Herschel, were authentic clusters. He detected multiple galaxy clusters using the 48-inch Schmidt telescope at Mount Palomar Observatory. Between 1937 and 1941, Zwicky discovered 18 supernovae in external galaxies, whereas the total discoveries by all other astronomers reached 12. In 1934, Zwicky and Baade collaborated on a significant prediction in the history of astronomy. They noted several substantial events in physics: the progression of quantum theory, the discovery of the neutron, the growing comprehension of stellar evolution. An important unresolved mystery at that time was the nature of cosmic rays, charged particles originating from outer space that reach Earth. The source of cosmic rays is still unknown. They suggested an alternative, rejecting the dominant theories of the era. The energy and irregular distribution of cosmic rays indicated a more sporadic source. What if cosmic rays emanated from supernovae, the terminal phases of massive stars undergoing gravitational collapse? The collapse of matter into denser states generates energy, clarifying the intensity of cosmic rays. The immense explosion generated enough energy to create the observed cosmic rays. Baade and Zwicky made further advancements. A byproduct of such a supernova would be the emergence of an atypical new type of star. We cautiously assert that a supernova signifies the transformation of a typical star into a neutron star, predominantly composed of neutrons. A star of this type may possess a small radius and an exceptionally high density. Neutrons can be more densely packed than conventional nuclei and electrons. This indicates that the gravitational packing energy in a cold neutron star can become exceedingly high. And in certain instances, it may significantly exceed typical nuclear packing fractions. A neutron star exemplifies the most stable configuration of matter. Every small radius was measured at several tens of kilometers, 100 times smaller than that of a white dwarf. Chadwick's 1932 discovery of the neutron inevitably concluded that the nuclear forces in stars, proposed by Eddington, were merely the beginning. From the extinction of colossal stars arose a new manifestation. When neutrons were liberated from the electromagnetic attraction of electrons and protons, which prevented white dwarfs from collapsing, they allowed dense stellar cores to undergo further gravitational collapse. The journal Physical Review published the structure of neutron stars in 1939. J. Robert Oppenheimer, an American, and his pupil George M. Volkoff were the authors. The individual directed the Manhattan Project, utilizing the penetrating characteristics of neutrons to create. Notwithstanding the intrigue surrounding neutron stars, the difficulty in their observation remained. Identifying a white dwarf proved difficult. Neutron stars are several hundred times smaller and considerably dimmer. Identifying the first white dwarf had pushed optical technology to its extremes. No one could devise a technique for identifying an object as elusive as a neutron star. As a result, the neutron star was destined to remain a theoretical anomaly for over 30 years. Nonetheless, as is often the science case, their discovery was not based on theoretical advancement, but rather on the unexpected evolution of technology, which revealed new insights into the universe. The night sky acts as a gateway to the universe. Air molecules scatter daylight, hindering our visibility. For astronomers, it is akin to attempting to watch a film in a theater with the lights on. As the sun descends, the sky dims, unveiling Earth's cosmic environment. Since prehistory, humans have viewed the night sky as a hemispherical dome with fixed stars. However, modern comprehension indicates that this dark canopy is deceptive, enabling exploration of the cosmos. The variation in the perceived brightness of stars arises from a combination of intrinsic luminosity and distance. Generally, the fainter stars are situated at greater distances. As the distance we observe increases, the prevalence of stars also escalates. Ultimately, they forfeit their individuality and merge into the ethereal collective of the Milky Way, similar to how grains of sand coalesce to form the uniform expanse of a beach. Visible diffuse patches are galaxies situated at great distances from our own. As technology advances, our comprehension develops, yet there seems to be no conclusive boundary to our discoveries. The sky has no surface or boundary. When we look into the night sky, we humbly, yet inevitably observe the universe. Nonetheless, the universe comprises more than what is observable. An imperceptible domain exists beyond our innate senses. And this new universe was unveiled fortuitously, similar to many notable scientific discoveries. Ironically, radio engineers pursuing triumph in a conflict first examined it, rather than astronomers committed to celestial observation. In 1932, notable advancements in science occurred. Chadwick identified the neutron, and Landau proposed the concept of the nucleus star. Additionally, radio became a dominant medium for communication and entertainment during that decade. Nevertheless, it faced numerous challenges. Bell Telephone Laboratories sought to employ radio transmissions for transatlantic telephony. However, a continual hiss obstructed what were regarded as short wavelengths, 10 to 20 meters. Carl Gunther Jansky, a young radio engineer who joined the company in 1928, identified the noise source. Although not considered an exceptionally notable profession then, the hiss he was investigating offered our first glimpse into the universe. The new window will reveal the Milky Way's structure and a variety of new astronomical phenomena, including pulsars. Jansky developed an antenna proficient in detecting radio waves with a wavelength of 14.5 meters. To facilitate his identification of the static source, he connected the antenna to a substantial turntable, which was named Jansky's merry-go-round. After months of observation, Jansky could distinguish static from proximate and remote thunderstorms. Nonetheless, he was captivated by a subtle yet persistent hiss that seemed to originate from an indeterminate source. Owing to the daily variations in static intensity, Jansky initially surmised that he was identifying static emanating from the sun. The Earth's rotation occurs every 24 hours, causes the sun to traverse the sky consistently throughout the year. After months of observation, it became apparent that the most luminous point was shifting, not in a regular 24-hour cycle like the sun, but in a shorter duration of 23 hours and 56 minutes. The remote stars undergo a daily loss of 4 minutes due to the Earth's orbit around the sun. The discrepancy was slight, but adequate to determine that the source was celestial and external to the solar system. The static identified by Jansky emanated from deep space. Initially, Bell Labs capitalized on the discovery and obtained significant publicity. When Jansky proposed the development of a 30-meter diameter dish antenna to further explore the phenomenon, he received no backing from his employer. Despite Jansky's fascination with space-based static, it posed no challenge to the operations of Bell Labs. They obtained their reply, thereby resolving the issue. After allocating an alternative project, Jansky ceased his involvement in radio astronomy. For years, researchers overlooked the radio sky. In 1934, a young Grota Reber examined one of Jansky's papers and believed he had found the means to conduct a more comprehensive investigation of the phenomenon. Constructing a parabolic dish will facilitate the observation of these peculiar radio waves with enhanced angular resolution, aiding in identifying their celestial origins. Reber submitted his proposal to Jansky. Yet Jansky's adverse reaction arose from ambiguous reasons that necessitated additional elucidation. Reber could have engaged with the astronomers more promptly. In a 1992 interview, he remarked, "The optical astronomers were oblivious to radio technology and consequently regarded Jansky as erroneous, whereas the electrical engineers recognized Jansky's research but considered it inconsequential. Nonetheless, not everyone dismissed it as pointless." Within a few years, Cambridge physics professor Gennady Potapenko and his student Donald Follard corroborated Jansky's findings using a loop antenna, and later a single-wire antenna in the Mojave Desert. 1936. Despite Jansky's discouraging reply, Reber constructed a 31.5-foot fully steerable parabolic dish in his parents' backyard. With the assistance of a local blacksmith, the total expenditure reached $1,300, allowing him to explore the radio sky at wavelengths of 74.9 centimeters, 400 megahertz, and 199.9 centimeters, 150 megahertz. Reber became the world's first and only radio astronomer with this equipment. Unfortunately, academics dismissed his work due to the lack of suitable university supervision. Two significant advancements were the identification of sunspot groups at radio wavelengths and the formulation of predictions through the detection of the crucial 21-centimeter line emission from hydrogen. The latter represented a significant breakthrough in clarifying the dimensions and structure of our galaxy. Many esteemed publications claim that looking towards Sagittarius enables observing the Milky Way galaxy's center. This implies that when I gaze downward at the Earth, I observe Greenland. We can modify our local geography as needed. Extensive interstellar gas and dust clouds isolate us from the rest of the galaxy, rendering the task of mapping our environment comparable to traversing a thick fog at night while donning sunglasses. In the mid-1940s, the distinguished Dutch astronomer Jan Oort considered the viability of studying interstellar hydrogen, which constitutes most of the galaxy's composition, at radio wavelengths. He tasked his student Hendrik van der Hulst with investigating the feasibility, and in 1945, van der Hulst delivered the solution. Hydrogen emits a specific spectral line at a wavelength of 21 centimeters. If a radio receiver were designed to detect exclusively this wavelength, hydrogen would be detectable, and the obscuring dust and gas of the Milky Way would become transparent. Van der Hulst formally submitted the proposal to Reber. Reber initiated the construction of an antenna for the project, but was later presented with an opportunity to join the National Bureau of Standards in Washington. He abandoned the endeavor. Harold Dock, Ewan, and Edward Purcell required 6 more years to ultimately identify the 21-centimeter line. With the obstruction of interstellar gas and dust finally eliminated, astronomers could delineate the galaxy's structure, revealing its spiral configuration. For the first time in history, astronomers could explore beyond the confines of the local stellar neighborhood and study the galaxy. Central to this narrative was the continuous enhancement of radio technology, facilitating the identification of discrete radio sources, small, easily distinguishable radio waves that are not part of the background noise. During the Second World War, radio technology underwent considerable advancement, and by the war's end, radio engineers in England, Europe, the United States and Australia were directing their attention and antennas skyward. The initial intense radio emissions from the Sun were unintentionally detected by British coastal radar stations during the war, and were erroneously attributed to German jamming activities. James Stanley. Hay investigated the phenomenon and correctly inferred that the Sun emits radio waves. In 1946, he conducted one of the inaugural meter-wavelength surveys of the celestial sphere. During this period, he discovered a luminous discrete radio source in the constellation Cygnus. However, he could not ascertain its location sufficiently to identify it optically. The preponderance of notable early discoveries transpired in Australia. John Bolton, Gordon Stanley, and Bruce Slee utilized equipment on the cliffs of Dover Heights, located on Sydney's eastern coast, which overlooks the Tasman Sea. Analogous to how the rising sun glistens on the water, each radio object appearing over the ocean's horizon generates a reflected image on the surface, creating two sources of radio waves that periodically enhance and attenuate each other. This phenomenon can be exemplified by dropping two stones into a calm pond and observing the two sets of waves as they alternately interfere with and amplify each other as they propagate across the surface. Radio waves display comparable characteristics. By configuring the radio antenna to capture both wavesets, the engineers accurately determined the space by analyzing the interference pattern's intensity, rise time, and regularity. This technique, interferometry, is poised to play an increasingly pivotal role in radio astronomy in the upcoming decades. The Dover Heights team prioritized re-identifying the source in Cygnus, as reported by Hay in 1946, and sought to ascertain a considerably more precise location for it. In June 1947, they recognized its C interference pattern and labeled the source Cygnus A. However, its location comprised only a few faint stars. Bolton and his team inferred that a unique radio source suggested the presence of supplementary sources, leading them to examine the skies with their C interferometer. On November 6, 1947, another source was discovered in Taurus, and by March 1948, an additional 6 sources were identified across the sky. Radio sources do not resemble stars. While individual stars are readily identifiable, the locations of radio sources could have been delineated with greater precision. Like Cygnus A, none of the other radio sources aligned with objects detected at visible wavelengths. Cygnus A, the most prominent of the sources, was identified in the early 1950s by a team led by Francis Graham Smith in Cambridge, whose more accurate location corresponded with a relatively faint nebulous region. Walter Bardy and Rudolf Minkowski conducted a spectroscopic analysis of the visible object at this location. They discovered that it was a galaxy, and that most of its energy originated from radio waves. In mid-1948, Bolton and Stanley travelled to New Zealand to improve the resolution of radio sources. They had 2 objectives. The sources over the Western Ocean horizon allow for a more accurate identification of their location. The second point is that New Zealand features cliffs of greater elevation than those on the east coast of Australia, and it was expected that the increased altitude would improve angular resolution, resulting in a clearer radio image. They transported an aerial on a large trailer and selected 2 cliff-top sites with elevations of approximately 300 meters, compared to Dover Heights at 79 meters. Despite the persistent severe weather conditions, 4 months of observation and analysis revealed the locations of 4 new sources within minutes of the arc, approximately 1/6 the diameter of the full moon. 2 sources corresponded with images of galaxies. Virgo A was discovered near M87, a substantial elliptical galaxy and the second most luminous constituent of the 2500 galaxy Virgo cluster. Centaurus A was identified as associated with NGC 5128, a significant source of X-rays, infrared and gamma radiation, and is the closest of the so-called active galaxies. Taurus, a tertiary radio source, is associated with the ancient supernova remnant called the Crab Nebula. The Crab Nebula derives its name from its shape, which loosely resembles that of a crab. The minute illuminated region, discernible through small telescopes, corresponds to the location of a new star recorded by Chinese and Japanese astronomers in 1054, who observed its visibility even during daylight for more than 3 weeks. Upon Bolton's discovery, the disparate components of stellar evolution commenced their convergence. The new star was a supernova, the explosive and tumultuous end of an aging high-mass star. Almost 900 years later, it persisted in emitting radio waves across the galaxy. Excluding the Sun, the Crab Nebula was the first visual object identified as a radio source, thus establishing John Bolton, Bruce Slee, and Gordon Stanley as the forerunners in associating radio sources with optical counterparts. This also indicated the advancement of radio astronomy, proving its capacity to produce discoveries wholly independent of optical astronomy. A new era in scientific research has begun. Australians were not the exclusive contributors to the nascent field of radio astronomy. John Ratcliffe, a distinguished expert in upper atmospheric physics, returned to Cambridge University in England after the war's end. During the war, Ratcliffe concentrated on radar research. Upon his return to Cambridge, he recruited several young radio scientists, including Martin Ryle, Francis Graham Smith, and Anthony Hewish. The men salvaged as much British and German radar equipment as possible over a year, and subsequently commenced radio observations. After observing sunspot emissions, the team focused on particular radio sources. While the Australians were the forerunners in identifying these sources, forming initial sky surveys, the British team conducted the first comprehensive sky surveys in search of new objects. The inaugural Cambridge survey, now consisting of 9 published surveys, utilised a technique termed phase switching, devised by Ryle. This necessitated receiving signals from 2 remote antennas and delaying one to synchronise it alternately with the other's signal. This technique streamlines the identification of point radio sources amidst the background. The Cambridge team effectively catalogued 50 sources using this technique. In 1952, 4 years later, Ryle led a team that utilised a double interferometer, consisting of 4 cylindrical antennas, at the corners of a large field, situated a few kilometres west of Cambridge. The astronomers documented 1,936 radio sources in the 2C catalogue, following a 3-year period. The third Cambridge catalogue, or 3C, pledged to unveil an entirely novel astronomical phenomenon. A specific category of radio source sets itself apart from all others. They appeared diminutive yet luminous when observed against the sky, akin to radio stars. Astronomers designated them as quasi-stellar radio sources, subsequently abbreviated to quasars. The resolution of a radio telescope is markedly inferior to that of optical telescopes, complicating the determination of the point-like characteristics of quasars and their exact positions. Both elements were clarified in 1962, when the Moon obscured the most luminous quasar, 3C27 3.5. While the Moon orbits the Earth, it obscures any celestial body farther away, a phenomenon termed lunar occultation. The Moon's absence of atmosphere results in a sharply defined edge, or limb, when viewed from Earth. When the moon occludes a point object, such as a star, the star vanishes abruptly, rather than gradually fading, as with objects possessing a measurable diameter like planets in the solar system. The method of lunar occultations was originally utilized to ascertain the moon's location. By accurately determining the positions of the stars, the moon's path could be precisely charted. Determining the precise location of the moon allows for the inverse. By recording the exact moment the moon obscures a radio source, one can ascertain the precise position of the radio source, facilitating its correlation with observable entities. Numerous efforts to identify these unusual radio sources resulted in minimal success in the early 1960s. The progress transpired in 1962 with the deployment of the 64-meter Parkes radio telescope in western New South Wales. Occultations of 3C273 are observable from the southern hemisphere every 20 years. Cyril Hazard, associated with the newly formed astronomy group at Sydney University, allocated time on the recently completed Parkes telescope to observe the events. The preliminary observation necessitated enhanced conclusiveness. An additional occultation of 3C273 remains unobserved due to a complication. The considerable diameter of the Parkes dish, juxtaposed with its relatively short support tower, limited the dish's tilt to 60 degrees from the zenith. An alarm triggers when the large dish reaches an angle of 30 degrees above the horizon and its rim approaches the ground, automatically ceasing the telescope's operation. The problem was that when 3C273 was scheduled to re-emerge from behind the moon, the two entities would be situated just below 30 degrees in the sky. This was a notable observation relevant to radio astronomers and the Parkes telescope. We expected the newly completed telescope to initiate operations with a notable discovery, and quasars presented considerable potential. Bolton and his associates would not permit a minor safety protocol to obstruct a potentially momentous astronomical discovery. Bolton deconstructed the telescope's safety features and employed a grinder to remove sections of the bearing housings, allowing the dish to incline an extra degree toward the horizon. To prepare for the observation, all access routes to the observatory were sealed. Non-essential electrical devices were disabled, and the electronic apparatus necessary for the observation was replicated. On the evening of August 5, 1962, 3C273 was obscured by the moon. Upon re-emergence, the Parkes telescope's edge was nearly in contact with the ground, yet it observed everything. The observations were so substantial that Hazard and Bolton returned to Sydney with duplicate copies of the event's records on different aircraft. Analysis of the radio observations revealed that 3C273 consisted of two separate points instead of a single one. Upon examining images of the region captured by the 200-inch Hale telescope, it was determined that the radio source was adjacent to a diminutive blue star, exhibiting a faint jet emanating from it. At this point, most astronomers hypothesized that these radio stars were anomalous stars located within the Milky Way, akin to other stellar entities. The following step examined this star, which appeared anomalous in images and demonstrated strong radio emissions. We examined stars through their spectra. Martin Schmidt, a Dutch astronomer, utilized the 200-inch telescope, the largest globally at that time, at Palomar Observatory in the United States, to successfully obtain the spectrum of 3C273, thereby advancing the comprehension of quasars. Astronomers expected that examining the spectral lines would yield information regarding the star's composition, motion, and additional attributes. Upon reviewing the configuration of the lines, Schmidt deemed it incomprehensible. Comparing the line arrangements with those in tables obtained from observations of other stars produced no significant results. Is it conceivable that the star contains previously unrecognized elements? What occurred? Schmidt needed 4 months to determine the solution. Nevertheless, we must undertake a succinct astronomical digression to grasp Schmidt's perspective. For decades, it has been established that the arrangement of spectral lines in a star or galaxy's spectrum reveals its composition and velocity. Light demonstrates comparable behavior to sound regarding its motion. You may have encountered a vehicle equipped with a siren, such as an ambulance, that initially approached and receded into the distance. The siren produces a higher pitch as it approaches than when it recedes. The Doppler effect occurs due to the relative motion between the source of sound waves and the listener's ear. As the ambulance nears, the sound waves compress, generating a higher pitch. Conversely, as it moves away, the sound waves elongate, yielding a lower pitch. Like sound, light is composed of waves. Therefore, when a star moves closer to us, its spectral lines shift toward shorter wavelengths, specifically the blue end of the spectrum, akin to a higher pitch. As a star moves away from us, its spectral lines exhibit a redshift. Astronomers can specify the location and path of stars within the galaxy. A similar phenomenon occurs in galaxies distant from the Milky Way. Edwin Hubble was a trailblazer in the examination of galaxy spectra. Hubble systematically examined thousands of galaxies, recording and analyzing their spectra. His observations revealed two notable astronomical phenomena. Almost all galaxies beyond the Milky Way displayed a redshift in their spectra. This signified that they were retreating or distancing themselves from us. It is essential to avoid the misconception that the Milky Way is situated at the center of the universe solely due to the observation that all galaxies are receding from us. On the contrary, it asserts that we hold no distinctive status in the universe, and that every galaxy is receding from all other galaxies. The reciprocal recession of galaxies is often illustrated by imagining sultanas in a baking fruitcake. As the cake expands, each sultana moves away from the others, driven by the expanding cake. Hubble established a fundamental principle linking distance to recession velocity. The mutual recession of galaxies implies that a galaxy's recession velocity correlates directly with its distance from an observer. Examine 3 galaxies situated equidistantly along a linear path, all receding from each other at the same velocity. Imagine our existence in a galaxy located at one end of the continuum. From our perspective, the central galaxy will retreat from us, just as we will be moving away from its inhabitants. The recession of the more distant galaxy, located twice as far away, would occur at double the speed of the nearer galaxy. This transpires as it distances itself from the nearer galaxy and recedes from our position. A galaxy's recession velocity is directly proportional to its distance. The recession velocity is proportional to distance, yielding a nearly constant velocity-to-distance ratio among various galaxies. The Hubble constant has been exceedingly difficult to determine with precision. Accurately measuring distances to galaxies is extremely difficult. Nonetheless, it is indisputable that the galaxies were situated at a considerable. Hubble overlooked the theoretical foundations of the universe's expansion, whereas Albert Einstein demonstrated significant interest in the concept. General relativity redefined space not as an empty chessboard for maneuvering pieces, but as a tangible substance to which all entities are interconnected. Space's curvature, flexion, and extension influence the positioning and movement of all entities within it, akin to galaxies illustrated on a vast rubber sheet. The recession of galaxies did not signify their motion through space. Instead, it demonstrated their displacement due to the expansion of space itself. This was a notable prediction of general relativity that Einstein initially struggled to accept. His theory indicated a profound apprehension regarding the ramifications of an expanding or contracting universe, leading him to propose the esteemed cosmological constant that preserves a static universe. Einstein acknowledged the accuracy of his prediction, which excluded the cosmological constant, only after Hubble announced his discovery of the galaxy's recession. An object must be positioned significantly to perceive the effects of the universe's expansion. As a result, proximate entities like the stars in our Milky Way galaxy or the Andromeda galaxy, situated 2 million light-years distant, remain predominantly unaffected by the expansion of space. A high redshift indicates a considerable recession velocity solely over cosmological distances, thus signifying a significant cosmological distance. Before Schmidt analyzed the spectrum of 3C273, the most remote known objects were nearby galaxies, vast island universes that emitted light from their billions of stars collectively. Astronomers persist in contending with the enormity of the universe as clarified by Hubble's law. They continue to construct maps of the universe by measuring the redshift of individual galaxies, converting this redshift into distance, and plotting the spatial locations of the galaxies. We can now re-examine Schmidt and his remarkable discovery. In the 1960s, the quantification of a galaxy's redshift and distance was firmly established, prompting Schmidt to invest significant time in analyzing the spectrum of the quasar 3C273. After months of contemplation concerning the spectrum of spectral lines, he recognized that the lines he observed were produced by hydrogen, the most fundamental and abundant element in the universe. Their position in the spectrum perplexed him. They were situated closer to the red end than anything he had previously encountered. The pronounced redshift of the lines can be ascribed to a singular factor: considerable velocity retreating from the Milky Way, signifying that the object was at a significant distance. Schmidt recorded a redshift of z equals 0.158 at the rest wavelength, signifying a distance of roughly 2 billion light-years. To be observable from such a considerable distance, 3C273 had to possess exceptional brightness, either in visible light or radio waves. This indicated that it required an indeterminate quantity of energy. Quasars undeniably constituted a new category of astronomical phenomena that required the focus of astronomers. By the end of 1964, 40 quasars had been identified, with some displaying redshifts of 200%, indicating distances of 10 billion light-years, thus effectively doubling the perceived size of the universe. The proposal indicated that this merely reflected the superficial aspect of a more significant problem. This notable astronomical discovery necessitated further examination. If astronomers could not clarify its nature, they could at least pursue additional instances. The Cambridge group has exhibited expertise in constructing radio telescopes for radio sky surveys. The Cambridge surveys revealed progressively complex details. Quasars emerged as pivotal in the research, although their identification necessitated substantial effort. Ultimately, a limitation exists on the range of the sky traversed by the Moon, thereby constraining that particular identification method. Anthony Hewish, an astronomer who advanced radio interferometry at Cambridge, devised a method for identifying new quasars in the sky. However, it required a novel technique utilizing an innovative radio telescope design. He would necessitate aides to develop and execute his new design. Included in his staff was a young PhD candidate, Miss S. Jocelyn Bell. Jocelyn Bell cycled to the observatory as she had often done. The interplanetary scintillation array, designed by Hewish to identify quasars, resembled a vineyard rather than a scope, as it collected radio signals from space and recorded them as a series of fluctuating lines on a paper chart. Bell's responsibilities included providing the recorder with paper and refilling the ink wells for the recording pens. Her principal duty was to examine the recordings for signs of quasars. During that period, computers were available. However, experts argued that a proficient human could more accurately distinguish between interference and quasar signals, especially as astronomers became familiar with the telescope's operation. After analyzing roughly 100 meters of chart recordings, the 24-year-old PhD candidate achieved competence in her task. Bell incorporated and evaluated the substantial collection of paper chart recordings due to the impracticality of real-time monitoring and analysis of recordings. In August 1967, she noted what she would later describe as scruff on the recording. It resembled neither a natural signal she had experienced nor an artificial one. Mysterious. Although it was probably trivial, she marked it with a question mark and continued her examination of the recordings for quasars. Quasars were a groundbreaking and highly regarded astral phenomenon. These radiant radio beacons were as accurate as the stars but more distant than the galaxies. What can be so distant yet emit such brilliance? What could generate such immense energy that it permeated the expansive universe? The answers to these and various other questions maintained an interest in astronomy. However, the next logical step was determining the number and properties of quasars. The stellar appearance of quasars enabled a novel method for identifying further specimens. While observing the night sky and differentiating between the stars' radiant points and the few planets, you may have noted that the planets do not twinkle. The primary reason for this is that from Earth's perspective, the planets exhibit a small but noticeable diameter. Conversely, despite stars being significantly larger than planets, their distance renders them as mere points of light. The Earth's atmosphere refracts a light beam from a point source unpredictably. This slight light scattering causes the star's twinkling appearance in the sky. During the mid-1960s, researchers noted a significant twinkling in the images from point radio sources beyond the solar system. The Earth's atmosphere reaches a limited altitude in space, while a vast cloud of charged particles called the solar wind permeates the solar system. Visualize this particle flow not as a consistent stream, but as substantial, irregular aggregates of diffuse gas erupting across the solar system, producing tumultuous currents in various directions. Starlight is unaffected by the solar wind. Conversely, radio waves display distinct behavior. Radio waves experience diffraction while passing through the solar wind, a unique type of bending that differs from refraction. Nonetheless, the resulting effect is similar. It causes twinkling in radio sources, a phenomenon known as interplanetary scintillation. Compact radio sources display increased scintillation compared to extended sources, and lunar occultation observations have shown that quasars are significantly compact radio sources. Anthony Hewish concluded that a viable approach to identify additional quasars entailed surveying the sky for radio sources. Detecting those displaying variability could effectively locate more quasars. He would necessitate a radio telescope of exceptional sensitivity and resolution to achieve this. Hewish comprehended how to achieve both goals. Anthony Hewish engaged in radio operations during the war, concentrating on technologies to counter aerial radar at the Royal Aircraft Establishment and the Telecommunications Research Establishment, where he initially partnered with Martin Ryle. Ryle pioneered radio astronomy, was one of the first to perform interferometric radio studies, and was the chief architect of a team at Cambridge, originally known as the Radio Astronomy Group, now the Cavendish Astrophysics Group. They created the Cambridge catalogues of radio sources and discovered interplanetary scintillation. Hewish's wartime experiences with electronics and antennas, and an inspiring undergraduate course in electromagnetic theory propelled him to pursue radio astronomy. Driven by ambition, Hewish commenced his tenure at Ryle immediately following the war's interruption of his undergraduate education at Cambridge, where he obtained his PhD in 1952. Hewish swiftly made substantial contributions to the emerging discipline of radio astronomy. He was especially intrigued by the behavior of radio waves as they passed through transparent inhomogeneous media, including the solar wind. Hewish illustrated the application of interplanetary scintillation in producing high-resolution maps of the radio sky. Examining complex details in the sky requires telescopes with larger apertures, necessitating greater resources and labor. Hewish tackled the challenge by creating a phased array antenna that replicated the resolution of a 1,000-kilometer radio telescope and conducted daily surveys of the entire observable sky. The telescope, proposed by Hewish, would employ a novel method for identifying compact radio sources. This technique would identify rapid fluctuations in radio signals, distinguishing sources emitting light at radio wavelengths from the steady presence of extended sources. This method would improve the detection of quasars. He obtained funding for the telescope in 1965, which necessitated 2 years for completion. A quintet, including Jocelyn Bell, assembled the array. This radio telescope contrasts with the modern lustrous white dishes. During a summer break, several vacation students installed more than 1,000 vertical posts into the ground for Bebelland and her colleagues. They installed approximately 200 kilometers of wire and cables to establish 2,048 antennas. The entire array covered just under 2 hectares, equivalent to 57 tennis courts. They employ sheep to manage the vegetation around the array. Recognizing that such a complex arrangement of obstacles would present considerable difficulties for any lawnmower. This structure cannot align with different sections of the sky. However, this is irrelevant, as the Earth supplies the requisite orientation. Advanced electronic techniques allow astronomers to observe directly overhead and roughly 30 degrees above the horizon, as the Earth's rotation shifts the radio wave beam captured by the telescope across the sky. The IPS array was completed several months after Bell employed it to search for scintillating sources. She operated the telescope and analyzed the data under Hewish's supervision. As the radio sky moved overhead, the telescope analyzed 4 separate beams and recorded the results on 4 3-track pen recorders. Hewish's instructions were clear and precise. Analyze the recordings and record every significant source. I instructed Jocelyn to create a quick reference sky chart that records the position of each luminous source upon its emergence in the weekly logs, he explained. Authentic sources would consistently re-emerge at identical coordinates, while interference would occur randomly. My methodology for evaluating angular sizes required observations at different solar elongations, necessitating repeated measurements. Bell initially noted scruff roughly 6 weeks into the program. Subsequently, she noted further interference in the recording and recalled having previously encountered this type of signal. Upon examining prior records, she identified the original scruff and ascertained its celestial coordinates at right ascension, 1 hour, 19 minutes, 19 seconds. Although many may have considered the minute scribble mere interference, Bell recognized it as non-artificial. Furthermore, she was familiar with enthralling sources, and this specific one seemed to lack that attribute. Moreover, it manifested close to midnight in a region of the sky unaffected by the solar wind. Had it been a quasar, its scintillation would have been evident. Suspecting it to be a point source, Hewish conducted a more thorough investigation. The technique utilized with a radio telescope involved hastening the motion of the paper beneath the pens, thereby broadening the signal across a larger strip, similar to producing a photographic enlargement. Hewish instructed Bebello to install a rapid recorder to enable a more comprehensive analysis of the source during its subsequent occurrence. Hewish initially suspected that the erratic signal might originate from a flare star, requiring a faster chart speed for closer analysis. By October 1967, they had installed the last recorders and receivers and completed tests based on observations of the notable source 3C273. The IPS array is now completely functional. Bell regularly frequented the observatory to acquire prompt recordings of the object at right ascension 1919, yet he could not do so. After the initial observations, the source vanished. Bell recorded only receiver noise for several weeks. Hewish was concerned that the signal had terminated, admonishing Bell for regarding it as an isolated event and claiming that she had neglected it. In late November 1967, Bell, feeling exasperated, neglected her analysis to attend a lecture that seemed more engaging than her usual review of the recordings. Upon her return to the observatory the following day, she examined the recordings and discerned the scratch. Had Bell been present at the observatory that night, she would have witnessed its re-emergence. Bell continued to monitor her watch, driven by the signal's resurgence a few days thereafter. On this occasion, she recorded it during the brief session. As the chart developed under the pen, it became clear that the signals represented a series of pulses rather than a single-point source. After detaching the chart from the recorder, Bell placed it on the floor and employed a ruler to gauge the intervals between the pen marks. The captivating radio sources fluctuated for 1.3 seconds. November 27, 1967. Bell contacted Hewish, who was teaching at an undergraduate laboratory in Cambridge. His initial response was that the source must be artificial, as no known natural phenomenon could produce a recurring radio signal. Nonetheless, Bell sought elucidation on the rationale for excluding a star as the source. Hewish was sufficiently captivated to attend the observatory during the ensuing transit. Despite the playful interactions the source had with Bell during the frustrating weeks of October, it operated as expected this time. Precisely at the appointed moment, with Hewish and Bell observing intently, the pulses reappeared. Hewish examined the records, noting the timing of the source's emergence. The transit duration fluctuated nightly, signifying its adherence to sidereal time, the temporal measurement based on the stars. The signal emanated from outer space, rather than from Earth. They also ruled out alternative interpretations of the signal. Neither the Moon nor an artificial satellite in an atypical orbit was reflecting the signals. They rejected the idea that the effects stemmed from a substantial, corrugated metal structure located south of the telescope. Further analysis revealed that the signal was located beyond the solar system, yet still within the confines of the galaxy, regardless of its other characteristics. Furthermore, the source cannot be situated on a planet orbiting a star due to the evenly spaced pulses. If this were the case, the pulse period would fluctuate as the planet orbiting the star, a phenomenon known as Doppler shift. The planet compresses its pulses as it nears us on one side of its orbit, leading to a shorter period, and expands its spacing as it retreats on the opposite side. No variation was observed. Only a continuous sequence of exceptionally well-timed pulses was noted. This was undoubtedly an atypical astronomical occurrence. Using an alternative telescope and independent observers, we determined that this new object was not linked to the IPS array. We consulted Paul Scott and R.A. Collins to validate their findings utilizing a different telescope. As the transit time approached, Scott, Collins, Hewish, and Bell convened around the recorder. Upon inspection of the pens, they noted none. The pens exhibited stability, no deterioration occurred. Hewish, Bell, and Scott left. Disappointed Cott continued to examine the pens. He suddenly declared, "Here it is." The others rushed back to the recorder where the signal was detected. The scientists nearly discontinued their efforts prematurely, due to an error in calculating the source's transit time at the new site. Ultimately, Hewish and Bell validated the existence of the pulsating radio source. It was genuine, distinct from any previous observations. The inquiries concerned whom to inform and the means of notification. Making a novel discovery of this nature is exhilarating and uncomplicated. Discover something innovative, then promptly proceed to the newspapers. Science operates uniquely. It demands a meticulous balance between the necessity for prominence in scientific publications and the need for validation. The concluding factor incited the original controversy surrounding the discovery by Hewish and Bell. They discovered a novel finding but required clarification or validation. The challenge with this novel pulsing radio source lies in its inconsistencies. The rapid pulses suggested that the source was likely small. Stars are significant entities, and their periodic variations typically occur over extended periods, ranging from several days to months or years. Ultimately, there is the constraint that no entity in the universe can surpass the speed of light. If the sun were to suddenly stop emitting light for an unknown reason, it would not extinguish immediately but would gradually fade over approximately 1 second. The sun's diameter is roughly 1.3 million kilometers, causing the final rays of light from its far side to take approximately 1 extra second to reach us compared to those from its near side. The inability to exceed the speed of light implies that an entity oscillating at such a rapid frequency must be extraordinarily small. The notable accuracy of the period indicated it was significant and methodical. According to Bell's later remarks, it resembled a double-decker bus navigating on a sixpence. It was irrational. Furthermore, astronomers identified the ability to artificially produce rapid, precise pulses at a frequency characteristic of signal generators. The amalgamation of artificial and celestial sources poses a significant scientific risk. Scientists had to be discerning and thorough to avert the announcement of a fraudulent discovery. The undertaking necessitated substantial time and effort. However, it involved more than mere scientific rigor. We must briefly examine several decades to fully understand the Cambridge team's reluctance to reveal the discovery. A schism emerged between the radio astronomy teams at Cambridge and Sydney during the 1940s and 1950s. The crucial event influencing Cambridge's decision to withhold the pulsar discovery occurred in 1957. 2 years ago, Martin Ryle, in the presence of the Vice-Chancellor of Oxford University, explained the cosmological implications of the second Cambridge catalogue of radio sources, which includes around 1,700 radio sources. During that period, controversy remained concerning the steady-state theory posited by Fred Hoyle, Herman Bondi, and Thomas Gold, as opposed to the Big Bang theory. The steady-state theory asserts that the universe is infinite and immutable. In contrast, the Big Bang theory asserts that the universe emerged from a singular event at a particular moment and has evolved ever since. Ryle established that the 2C indicated a notable increase in radio galaxies with distance, thereby disproving the steady-state theory since greater distance suggested observing the past more extensively. If the steady-state theory were correct, the number of radio galaxies observed in the past, and consequently at greater distances, would be equal to that in the present proximal universe. Simultaneously, Joseph Pawsey's team in Australia was cataloguing radio galaxies. After examining 1,030 objects, the Sydney group identified no substantial discrepancy between the observed galaxy count and the projections of the steady-state model. Despite the eventual decline of the steady-state model, the Australian findings directly opposed those presented by the Cambridge group. The definitive explanation for the origin of the universe was in contention. Rudolf Minkowski from Mount Wilson and Palomar Observatory travelled to Sydney and Cambridge, spending weeks analysing both data sets to address the problem. He composed a comprehensive memorandum contending that the interpretation of the Cambridge data was inherently flawed and that the Australians were accurate. In March 1957, the Australian group published a paper critiquing the Cambridge survey. They were unambiguous, concluding with, "The Cambridge survey was significantly influenced by instrumental effects, while the Sydney results were only marginally affected. Thus, the majority of inaccuracies in the Cambridge catalogue. This analysis fails to support any cosmological conclusions. The Cambridge survey necessitated enhanced resolution. resulting in ambiguity among individuals and weaker multiple sources. The Cambridge astronomers sought to derive excessive information from the data, necessitating revision. The subsequent 3C survey, while considerably more comprehensive, necessitated concordance with the Australian results. Contrary to Hoyle's theory, evidence continued to suggest a significant excess of weak, more distant sources. Nevertheless, their reputation had already endured significant damage. These eminent scientists made an error and encountered the consequences. They were disinclined to replicate the action. They required verification of these flickering, pulsing radio sources' authenticity before public announcement. A major obstacle in pulsar discovery was their apparently artificial traits. All evidence pointed to a celestial origin. However, the combination of celestial and artificial elements implies the presence of extraterrestrial entities. Decades later, Carl Sagan articulated this scientific dilemma. Extraordinary claims necessitate extraordinary evidence. Shortly before Christmas in 1967, Bell intervened during a meeting between Hewish and Ryle, discussing the potential public announcement of the discovery if Hewish's current Doppler shift measurements indicated a planetary origin. Hewish remarked, "At that point, extraterrestrial intelligence, ETI, was still a plausible consideration in my view. Concurrently, no evidence supported that the signals were of natural origin." Humorously, Bell labelled the source LGM1, denoting Little Green Man 1. Who would be the first to determine this information if the signals were derived from extraterrestrial intelligence? What is the protocol for issuing such an announcement? The discovery, in fact, provoked Bell's ire. I was endeavouring to secure a PhD, utilising an innovative method, when some insignificant extraterrestrial entities chose my antenna and frequency for communication. Undeterred, Bell proceeded to the laboratory after dinner that evening to analyse the continuous chart recordings further. She subsequently located a scruff patch at RA 11 hours 33 minutes. She examined the records and confirmed the signal. Although she left the laboratory before its closure for the evening, she confirmed that the source would be visible through the telescope later that night and decided to examine the second source. The temperature was freezing upon our arrival at the telescope in the early hours of the following morning. The system experienced a significant reduction in gain at low temperatures. By manipulating switches, vocal commands, and exhalation, I attained optimal functionality for 5 minutes, specifically on the designated beam setting, Bell. This interference was subsequently presented as a series of pulses occurring 1.2 seconds apart. This represented a pivotal opportunity for Bell. It was highly improbable that two extraterrestrial groups communicated with Earth simultaneously, and at similar frequencies, despite originating from distinct spatial locations. Bell positioned the chart recordings from the second source on Hewish's desk, and departed for Christmas with a more optimistic outlook. Hewish continued the survey throughout Christmas, replenishing paper and ink while arranging the paper chart recordings on Bell's desk for her review. Hewish continued to perform daily timing measurements for the critical Doppler data. Hewish remarked, "I withheld commentary until I dismissed the extraterrestrial intelligence ETI hypothesis. Upon B. Bell's return from vacation, she could not find Hewish and continued to review additional recordings. Upon identifying her objective, she promptly found two supplementary sources. One at right ascension, 08 hours 34 minutes, and another roughly 1 hour away at right ascension 09 hours 50 minutes. She authenticated all three new sources within a few weeks. Bell scrupulously scrutinized the documentation from the IPS array, which now spanned several kilometers of paper charts. Although several candidates were identified, none were as advantageous as the original four sources. In late 1967, speculation regarding the Cambridge Group's extraordinary discovery was widespread within the astronomical community. Max Komisarov, a participant in the Parkes group, later reported that an informant had disclosed to him that the Cambridge group was detecting signals from outer space. Initially startled, Komisarov regained composure upon realizing that the entirety of astronomy was indeed receiving signals from outer space. Komisarov stated that upon the announcement, it was disclosed that they had not been intercepting Morse-coded communications for Centauri or the Andromeda Nebula. Yet their narrative was only slightly less remarkable. Nevertheless, the Cambridge radio astronomers opted to conceal the information. During a customary Friday luncheon in Cambridge, attended by scientists from various related disciplines, the radio astronomers abstained from contributing to discussions regarding their research. In February 1968, it was announced that Anthony Hewish would conduct a seminar on identifying a new category of pulsating radio sources. On February 20th, 1968, scientists began to enter the Maxwell Theatre at the Cavendish Laboratory. Seated at the rear, they presumed that all astronomers in Cambridge, including the controversial Fred Hoyle, were present. They awaited Hewish's announcement while seated attentively on the wooden benches. Hewish revealed all the information. Almost all. His team had detected a swiftly oscillating radio source without an apparent rationale. The audience was unaware of the sources. Despite the initial speculation about extraterrestrial intelligence, it was clear that they had identified a new astrophysical phenomenon. The audience regarded this as the commencement of a significant advancement in astronomy. Hewish summarized the paper, indicating that similar objects have been discovered in other areas of the sky. We contemplated these objects, and Hewish suggested a pulsating white dwarf. Fred Hoyle posited alternative theories. With his distinct Yorkshire accent, he articulated that he was unacquainted with these objects, but surmised they were supernova remnants rather than white dwarfs. He alluded not to the expanding gas clouds, but to the remnants of Barday and Zwicky's neutron star. Bell stated, "Considering the hydrodynamics and neutrino opacity calculations he must have conducted mentally. That is an exceptional observation." In his autobiography, Astronomer by Chance, Bernard Lovell detailed his reaction to the information obtained after the Cambridge seminar. Hoyle joined Lovell while anticipating initiating the Science Research Council meeting in London, taking the unoccupied seat to his left. Hoyle had recently returned from the United States, where the primary focus in astronomy was quasars, specifically using large American telescopes to measure redshifts. Lovell queried Hoyle about any developments. "I lack expertise in quasars," he replied, "but at a colloquium in Cambridge last night, Tony Hewish announced the discovery of radio sources emitting pulsed signals at roughly 1-second intervals." Lovell voiced skepticism, promptly proposing that the signals were probably due to interference. Hoyle notified Lovell that the Cambridge team had been examining the sources for several months, and that the evidence indicating an extraterrestrial origin of the pulses seemed persuasive. Lovell returned to Jodrell the following day and was astounded to learn that, despite our strong affiliations with Cambridge, this was the first instance of anyone possessing prior knowledge of this discovery, pulsating radio source. Hewish and his team maintained a veil of security and confidentiality concerning their work for several months, a significant accomplishment in an era of instantaneous communication among astronomers. 1 week later, Nature released a publication declaring the discovery. After merely 3 hours of observation, it ruled out the possibility of interference. These represented a novel astrophysical phenomenon. The Cambridge group delayed disclosing the source's location for an extra 2 months. A strategy that frustrated astronomers worldwide who were eager to initiate their own observations. Nonetheless, the revealed location of the 4 sources was imminent. During that time, Francis Graham Smith, an astronomer at Jodrell, subsequently succeeded Martin Ryle as Astronomer Royal in 1982. After receiving information from Lovell, I contacted Hewish and suggested that we could more effectively investigate the four sources using the 250-foot telescope, he recounted. He indicated that the positional measurements of the other three had not yet been finalized. However, within a day he supplied the positions, enabling us to initiate observations. Alan Sandage at Palomar Observatory also determined the position. Lovell communicated the positions to Hoyle, who then conveyed the information to Margaret Burbidge, who is affiliated with the University of California at San Diego. Subsequently, observers and theorists worldwide commenced their analysis of the objects. Jodrell Banks' superiority over Cambridge resided in its ability to observe the pulsar continuously while it was above the horizon, whereas the Cambridge telescope could only track the pulsar for a few minutes each day as it passed through the telescope's beam. Nature published a second paper on pulsars within 2 weeks. Unexpectedly, Bell terminated her association with pulsars at this point, assigning the observations to the next group of research students. She finalized her chart recording analysis, quantified the diameters of diverse radio sources, and composed her doctoral thesis. She added the discovery of pulsars, which would attract both acclaim and controversy. Notwithstanding her recognized scientific contributions such as pulsars, Bell's early notoriety occupied a tenuous space between comedy and tragedy, a distinction seemingly designated for the mainstream media. The Nature paper suggested a binary companion or planetary origin for the signals, garnering immediate media attention. They subsequently determined that a woman was involved. A century after Fleming, Maury, and Cannon systematically documented stellar spectra for their male superior, newspaper journalists questioned this remarkable young scientist regarding her height compared to Princess Margaret and the number of her romantic partners. Bell recalls being captured in numerous ludicrous positions: standing on a bank, seated on a bank, standing on a bank while scrutinizing imaginary documents, seated on a bank while reviewing fictitious records, and sprinting down a bank with her arms elevated. Unfortunately, the situation has not markedly improved. In 2004, Bell Burnell underscored the urgent need to augment the representation of female scientists. Observing progress in pulsar research over the last 36 years has greatly pleased me. The advancement and recognition of women in astronomy could have been significantly improved. In December 2003, the International Astronomical Union, IAU, published an evaluation of its membership. The United Kingdom and the United States markedly underperform compared to the international average, with only 10% female representation. The only change since a similar survey was conducted around 5 years ago was a slight increase in proportion across most countries. Senior astronomers are primarily members of the IAU, whereas a larger percentage of women hold junior positions. At the present rate, it will take 50 years for the proportion of female senior astronomers to reach 50%. The pipeline has been compromised. A higher proportion of females than males resign at every hierarchical level. Nevertheless, the media made a unique positive contribution to the discovery. A science journalist from the Daily Telegraph questioned the astronomers regarding the nomenclature of the newly discovered objects. Despite the pressing issues faced by Hewish, Bell, and their colleagues, the journalist suggested that they be classified as pulsars due to their nature as pulsating radio stars. The title remained unchanged. Nevertheless, the work science initiated by Bell and Hewish was engulfed in controversy and dissatisfaction. In examining the scientific progress concerning pulsars, it is essential to acknowledge that the assignment of credit for scientific discoveries is frequently unclear, with the acknowledgement of the pulsar discoverer exemplifying this ambiguity. The 1974 Nobel Prize in Physics was conferred for pioneering research in radio astrophysics. That year, the award was granted to two individuals: Martin Ryle for his observations and inventions, particularly the aperture synthesis technique, and Anthony Hewish for his crucial contribution to discovering pulsars. Jocelyn Bell was not recognized, leading to significant scrutiny concerning her exclusion. During that period, one individual exhibited superior articulation compared to others: Fred Hoyle. Simon Mitten's biography of Hoyle provides a detailed account of the incident. Nonetheless, a succinct summary will clarify the events and articulate concerns about the Nobel Prize conferred upon Hewish. Hoyle was in the United States, delivering lectures at various institutions. Hoyle was a notable scientist, already a figure of considerable controversy within the scientific community and widely popular among the public. His remarks to a journalist from a Montreal newspaper understandably garnered significant attention. After a conference on quasars, reporters sought his views on the Nobel Prize conferred upon Hewish and Ryle. Hoyle contended that Jocelyn Bell, not her supervisor Hewish, was the true discoverer and deserved acknowledgement. This represented a direct critique of the Nobel Foundation, and was tantamount to Hewish's accusation of academic misconduct. Hoyle criticized the Cambridge Group's initial reluctance concerning the discovery. In their typical fashion, the media magnified Hoyle's comments, suggesting that he accused Hewish and his senior colleagues of usurping Bell's discovery. Hoyle quickly acknowledged the seriousness of his remarks and conveyed his apprehension to his colleague Don Clayton from Rice University, indicating that if Hewish initiated legal proceedings, he might risk losing everything. Ryle and Hewish reacted swiftly and resolutely. This accusation infuriated and bewildered Hewish, who could not determine Hoyle's origin. Hewish considered initiating legal proceedings. However, Hoyle's letter to the Times, which clarified his views and pledged to cease further criticism of the Cambridge Group members, settled the issue. In a letter to the Times, he commended her engagement in the discovery, highlighting her great persistence in investigating the ostensibly questionable signal that ultimately confirmed to be a pulsar. The importance of Miss Bell's achievement has frequently been underestimated due to its seemingly simple nature. Sifting through numerous records, the achievement stemmed from a willingness to entertain a substantial possibility, a phenomenon that previous experience suggested was unachievable. To exemplify a comparable scientific advancement, I must cite Henri Becquerel's discovery of radioactivity. Hoyle considered Bell more than a simple employee. She had exhibited genuine acumen. In discussing the episode with Hewish, he emphasized that a widespread myth, particularly in the United States, suggests that Bell independently made the discovery while he was merely a bystander. Hewish's vast expertise with radio telescopes and his innovative design of an instrument adept at detecting rapid fluctuations in radio signals led to the discovery of pulsars in 1967. Before that, the design of radio telescopes concentrated on mitigating complex and sporadic interference by enhancing radio signals. The IPS array's inherent ability to detect rapid changes in radio sources made it ideal for pulsar identification. Astronomers utilizing a similar instrument in the Australian outback would not independently discover further pulsars for several months. Hewish recalls Bell as a diligent graduate student, although she did not participate in planning the sky survey for scintillating quasars or the design of the IPS array. Her duty was to oversee the survey's functioning and evaluate the recordings. Jocelyn needed the experience to initiate further observations, including accurate timing, distance assessments, or Doppler measurements, to rule out the possibility of extraterrestrial signals from an exoplanet. After the university term ended, I acted independently while Jocelyn examined past records for further potential pulsars, ultimately discovering 3 additional ones. I wrote the discovery paper, determining that neutron stars were the likely source of the pulses. As a result, I was profoundly involved in the process. The Nobel Committee has formally recognized that it meticulously assessed our contributions before conferring the prize upon me. An illustrative analogy is the discovery of America, credited to Columbus rather than the lookout who alerted from the masthead. In my Nobel lecture, I explicitly acknowledged Jocelyn's contribution and designated her as the second author of our paper. The Nobel Prize was justified. What was Bell's perspective on this issue? Bell asserted in 1977. Initially, conflicts regarding delineation between supervisors and students are persistently challenging and irreconcilable. The supervisor holds final accountability for the project's success. Sometimes, a supervisor assigns blame for a failure to their student, despite it being primarily the supervisor's responsibility. He should also enjoy the benefits of the successes. Thirdly, awarding Nobel Prizes to research students would be inappropriate unless exceptional circumstances exist, and this is not one of those cases. Ultimately, I am not dissatisfied with it. After all, I am in esteemed company, am I not? No. Nearly 30 years later, she penned a significant article for the journal Science, in which she provided the following commentary. I could argue that my identity as a student and gender substantially hindered my chances of obtaining the Nobel Prize, alongside Professors Anthony Hewish and Martin Ryle. During that time, individuals held the conviction that prominent figures, leading teams of unrecognized subordinates, undertook scientific pursuits and contributed exclusively as instructed. Despite my exclusion, I celebrated the first award of the Physics Prize for an astronomical discovery in 1974. I now recognize our enhanced understanding of the collaboration necessary for scientific progress. Identifying a new astrophysical phenomenon is essential, as it may provide new insights into the intricate mechanisms that govern the universe. The effort to understand pulsars had only just begun. Pulsars are expected to attract prominent scientists. The term controversial is almost synonymous with brilliance. Pulsar astronomy was ready for advancement. The late astronomer David Allen aptly described the most remarkable characteristic of pulsars: their swift rotation. Imagine, he once stated, that you are witnessing a pulsar rotating on a pedestal. Place a mark on the lateral surface of the pulsar near its equator. Determine the speed necessary to match that mark if the pulsar completes one rotation per minute. To traverse a diameter of 20 kilometers, one must maintain a speed of approximately 3,700 kilometers per hour. He stated, "Pulsars do not rotate once per minute." Researchers detected the first pulsars within seconds, and it would not be long before they discovered even faster variants. Astronomers found spinning pulsars difficult to accept, necessitating prolonged contemplation. An alternative explanation must exist. 4 months after the Cambridge announcement concerning the discovery of pulsars, their true nature persisted as an enigma. Astronomers worldwide, including various original discovery teams, convened in New York for a 2-day conference to discuss the matter. The event was methodically orchestrated by the Canadian-American astrophysicist A.G.W. Al Cameron, a scientist who devoted years to authoring theoretical papers on the unsubstantiated neutron star. Notwithstanding its lofty goals and distinguished attendees, many astronomers regarded the conference as a fiasco. The discussions focused on the concept of vibrating white dwarfs, a theory discredited by the year's conclusion, leading to some astronomers being misinformed by false alerts concerning detecting pulsars in visible light. Nonetheless, the most notable aspect of the conference was the rejection of the ultimately correct explanation of pulsars' nature. In the original discovery paper, Hewish underscored that the extraordinary regularity of the pulses is the most significant factor to consider. He suggested that regular pulsations are more likely attributable to a stellar-wide phenomenon than an isolated event in the star's atmosphere. At the conference, 3 primary explanations for the pulsating radio sources were presented: oscillations, orbiting planets, and stellar rotation. The most promising cause was oscillation, defined by a consistent and rapid reciprocal vibration. A newly struck bell illustrates oscillation, vibrating to produce sound. Astronomers suggested that stars may oscillate, emitting electromagnetic energy waves instead of sound waves, which they detected as radio pulsations. The oscillation frequency of a star is dictated by its mass, gravitational force, radius, and elasticity. It was previously thought that ordinary stars could not oscillate in this manner. However, two categories of stars may encompass white dwarfs and neutron stars. In the previous year, Al Cameron published a paper in Nature linking the newly discovered celestial X-ray sources to the unverified neutron stars and supernovae proposed by Bade and Zwicky. The problem was that calculations suggested neutron stars, if they existed, would oscillate up to 1,000 times faster, with periods between 10 and 1 milliseconds, thereby excluding them as no pulsations at that frequency had been detected. White dwarfs oscillate between 10 and 1 second, as demonstrated in Justice Pulsar identified at the conference exhibited a quarter of a second, substantially shorter than theoretical predictions. White dwarfs continued to be regarded as viable and the most likely candidates for pulsars. Nonetheless, alternative explanations are available. The radio pulses originated from a planet orbiting a star. Planets demonstrate shorter orbital periods with increased proximity to the parent star. Earth necessitates 365 days to complete a single orbit around the Sun, while Mercury, the solar system's innermost planet, accomplishes its orbit in 88 days, owing to its proximity, reduced distance, and elevated orbital velocity. This swift orbit must circumvent the Sun's gravitational pull. Astronomers identify rapid radio pulses that coincide with the planet's orbit around a star, measuring its year in seconds. The immense velocities indicated exceedingly small orbits, enabling ordinary stars to swiftly annihilate any planets nearby. If a planet emitting radio beams were to orbit the Sun at a sufficiently small radius, it would be located beneath the Sun's surface. Improbable. A white dwarf, with the mass of a star compressed into dimensions akin to Earth and measuring 1,000 times smaller than the Sun, would still be excessively large. A planet orbiting a white dwarf with a period of 1 second would have to be close to its surface. It seemed more feasible for a planet to orbit a considerably more compact neutron star, which is hundreds of times smaller than a white dwarf. Nonetheless, complications also emerged in this context. The orbit needs to be more stable. The system's energy, consisting of the planet and star, would gradually dissipate into space as gravitational radiation, slowing the planet and causing its spiral descent into the neutron star within a few hours. Before that event, tidal forces would have obliterated the planet. Even a planet made of high-tensile steel would necessitate a diameter of less than 20 meters to withstand the tremendous forces near a neutron star. Even if the planet continued to maintain its orbit, what could produce its radio waves? An alternative explanation must exist. The conference necessitated a more comprehensive examination of the concept of rotation. Can a rotating object produce the periodic radio emissions observed from CP1919 and analogous entities? Ultimately, rotation is one of the universe's most consistent and predictable phenomena. The grand rotation of the Sun and planets on their axes alongside the rotation of galaxies illustrates a simple mechanism for creating a repetitive occurrence. The question is, what could be rotating at such a high velocity? The maximum rotational velocity of a spherical object depends on its mass and diameter. A smaller object of a given mass exhibits greater density. Conversely, a denser object can rotate more rapidly without disintegration. A prime example of this is the planet Jupiter. With a diameter 12 times greater than Earth's and a mass surpassing 300 times, this extraordinary planet completes a rotation on its axis in less than 10 hours. Nevertheless, owing to its low density, the planet exhibits a flattened appearance akin to a deflated beach ball, a configuration referred to as an ellipsoid. If the planet were to rotate at an elevated velocity, it would disintegrate. Pulsars, rotating on timescales of seconds, require a more robust composition than standard planets or stars to maintain their structural integrity. The most preferred candidate was the diminutive, substantial, and exceedingly dense white dwarf. It was also comprehensible how a white dwarf could attain such elevated velocities. White dwarfs signify the degenerate cores of stars analogous to the Sun. All stars, including the Sun, rotate approximately once a month. Upon the conclusion of their lifespans, stellar cores commence collapse, converting their former majestic rotation into a chaotic spin. The conventional analogy features an ice skater who initiates a spin with her arms extended, and subsequently accelerates her rotation by drawing her arms inward toward her torso. Upon the conclusion of their lifespans, stars undergo a similar phenomenon. The core contracts to diminished diameters, conserving angular momentum and leading to an increased rotation of the core. Studies demonstrate that white dwarfs may rotate with periods as short as 1 second. At this velocity, the white dwarf would become an ellipsoid, expanding at the equator and losing mass in a circumferential disk. Any increase in speed would lead to its disintegration. Even if a rotating white dwarf could maintain its structural integrity at such velocities, it would still be incapable of elucidating the origin of the radio pulses. If white dwarfs lacked adequate density, only neutron stars would attain the necessary density. The identification of the neutron validated its existence. Neutron stars have considerable mass between 0.2 and 2 solar masses, while compact, with roughly 10 to 20 kilometers in diameter. These attributes suggest densities between 10 to the power of 14 and 10 to the power of 15 grams per cubic centimeter. A sugar cube composed of neutron star material would possess a mass of 100 million tons. Thomas Gold and Franco Pacini officially introduced the rotating neutron star model. 6 months prior, Pacini initially presented his concepts, and Bell's declaration regarding the existence of pulsars elucidated that neutron stars, which were merely theoretical at that time, would originate from supernova explosions and retain substantial energy in the forms of heat, vibration, magnetism, and rotation. Pacini questioned whether the energy release facilitated the excitation of supernova remnants, including the Crab Nebula. We will re-examine this remarkable object later in the book. Pacini believed that heat and vibration were inadequate sources for supernova remnants. He stated that investigating how a neutron star can dissipate its magnetic or rotational energy would be more intriguing. We posited that intense magnetic fields would surround neutron stars. Magnetic fields exist in typical stars, but they undergo considerable compression during the collapse of a massive star into a neutron star. Magnetic fields have a north and south pole, with the line connecting them known as the magnetic axis. The rotation axis typically misaligns with the magnetic axis of celestial bodies, causing the magnetic axis to oscillate in space during the rotation of the star or planet. Pacini stated that the same principle applies to the magnetic field surrounding a neutron star. The magnetic and rotation axes are unlikely to maintain perfect alignment throughout the star's collapse, even if they were initially aligned. This is because supernovae are not precisely regulated occurrences. As a result, the neutron star's rotation at remarkable speeds causes the magnetic axis to oscillate similarly rapidly. Fred Hoyle, Jayant Narlikar, and John Wheeler previously asserted that the oscillations of a magnetic neutron star would generate radio waves. Nonetheless, Pacini's observation regarding the rapid attenuation of these vibrations dispelled this theory. Pacini posited that the oblique rotator model might also emit electromagnetic radiation. Furthermore, the radio waves would propagate at the same frequency as the neutron star's rotation. Regrettably, most observers, including Thomas Gold, have largely overlooked Passini's paper despite the necessity of familiarizing them with his concepts. Ironically, the two astronomers who occupied nearly adjacent offices at Cornell University when Gold composed his paper linking pulsars to neutron stars did not partake in theoretical discussions for unspecified reasons. At least, not during that period. At the time of the pulsar's discovery, Gold was the director of the Arecibo Observatory in Puerto Rico, the largest radio telescope globally, measuring 300 meters. Gold was an indisputably controversial figure. From the beginning, he demonstrated a talent for formulating theories across various scientific fields. Numerous concepts will exemplify the diversity of his thought. 1946, as a graduate student, he discerned a deficiency in a prevailing auditory theory and proposed an alternative, positing that the inner ear operates as an amplifier. 3 decades later, physiologists discovered the microscopic cilia in the inner ear, corroborating his theory. In 1948, he shifted from physiology to cosmology and partnered with Fred Hoyle and Herman Bondi to promote the now discredited steady-state theory concerning the universe's origin. Neil Armstrong's one small step confirmed his claim that a thin layer of dust would cover the moon. Following his life, he postulated regarding the origins of the Earth's petroleum reserves. Gold proposed that oil originated from primordial hydrocarbons present since the planet's formation, rather than from the remains of deceased organisms. This distinguished scientist developed the rotating neutron star hypothesis of pulsars. The New York conference rejected Gold's manuscript detailing his theory. Al Cameron was highly knowledgeable about neutron stars, having published numerous papers on their properties for years despite their status as theoretical entities. He suggested a correlation between neutron stars and X-ray sources 3 years ago. Nevertheless, after reviewing Gold's paper associating pulsars with neutron stars, Cameron refused to allocate 5 minutes to Gold at the conference. Cameron asserted that Gold's proposal was so egregious that, if accepted, it would require the endorsement of numerous analogous suggestions. Fortunately, John Maddox, the editor of Nature at the time, was inclined to acknowledge the scientific value of innovative ideas and sanctioned Gold's manuscript. The Nature offices published the manuscript in print within a week of its submission, possibly establishing a record for scientific publications. The essential components of the paper include the concluding paragraph before the credits. Gold predictions yield 2 results. Pulsars are expected to gradually slow down. Secondly, if pulsars were experiencing deceleration, one would expect to identify younger, more rapidly rotating pulsars. The extraordinary confirmation of these predictions transpired rapidly for Gold. A recently completed radio telescope in the Australian outback can transform the field. In 1968, Alan Vaughan, now a senior lecturer at Macquarie University in Sydney, began his PhD under the supervision of Michael Large. Michael Large published the paper elucidating the discovery of pulsars during the same week. Another faculty member, Tony Turtle, asked Vaughan if he would like to join him at the Molonglo Radio Observatory near Canberra, where he examined the 4 newly discovered pulsating radio sources. The primary instrument at Molonglo was the Mills Cross, comprising 2-mile-long slender radio antennas configured in a cross formation that produced a singular beam. Bernard Mills of Sydney University designed it, having previously built a similar instrument near Sydney. In November 1965, Bernard Mills established the Mills Cross to comprehensively examine radio sources. Vaughan enthusiastically took the opportunity to employ the Mills Cross with Turtle to observe the 4 pulsars. They then considered how to employ the telescope for additional discoveries. The Mills Cross telescope had a broad field of view, allowing it to survey large areas of the sky and detect pulsars that necessitated more accurate localization. Initially, Vaughan and Turtle employed the transit method to segment the east-west arm into an east arm and a west arm. They achieved this by marginally adjusting their angles to create a 1 or 2 degree declination, enhancing their sky visibility. Consequently, They could observe vast celestial areas moving away due to the Earth's rotation. Concurrently, Large and Vaughan contemplated a project to augment the sensitivity of the Mills Cross. Up to that point, the east-west arm of the Mills Cross produced a singular beam. Large and Vaughan conceived a device to generate a phase delay in two orientations along the east-west axis. This would generate two additional beams distinct from the central beam. One would precede it temporally, while the other would follow it. Integrating signals from the north-south arm resulted in three distinct observations of the mobile source, significantly enhancing the telescope's sensitivity. Vaughan took responsibility for constructing a device to accomplish this objective. Vaughan and Turtle initiated bi-weekly visits to the telescope, for roughly 1 week during each visit. Shortly thereafter, they identified the initial two southern pulsars, one of which exhibited approximately 0.25 seconds, demonstrating considerable sensitivity to pulsar intervals. Turtle emigrated shortly after these discoveries, enabling Vaughan and Large to continue their search. Subsequently, they recognized that employing 3 consecutive beams in the east-west arm, initially intended to enhance the telescope's sensitivity to all radio sources, was an effective method for detecting pulsars specifically. Interference constitutes a growing concern for all types of telescopes, including radio telescopes. Vaughan and his colleagues' challenge was distinguishing between the relatively weak pulsar signals and the background radio interference. Such interference may stem from distant thunderstorms or defective ignition systems in adjacent vehicles. The fundamental difference is that interference emanates from Earth, whereas pulsars are distinctly a celestial phenomenon. At that stage, the east-west arm recorded simultaneous transits from each source without distinguishing interference. The initial and final beams allowed astronomers to differentiate between a celestial point source of radio waves, background noise. The initial beam would first pass through a pulsar, succeeded by the subsequent beam as both beams concurrently documented interference. 2 distinct pens documented the signal from each beam onto the chart paper. If one pen exhibited a consistent sequence of pulses indicating a pulsar traversing one beam, and the other pen subsequently recorded it, the astronomers could definitively conclude the presence of a pulsar. This was pivotal to the inaugural extensive survey of the southern sky employing the Molonglo telescope. In the course of this survey, Large and Vaughan made a notable discovery. One weekend, Vaughan participated in a church camp while Large oversaw the observations. Coincidentally, Large had recently initiated an observational session one morning and was monitoring the chart recorder when it suddenly malfunctioned. One pen began to write vigorously on the paper, soon followed by the other. This was clearly a celestial event. Large perceived that a notable event had occurred and swiftly contacted Vaughan, who arrived promptly. The pair acknowledged that they had discovered a pulsar whose speed exceeded their chart recorders. Large also reached out to Bernie Mills, who verified the pulsar coordinates and disclosed a more captivating finding. It was near the core of the Vela supernova remnant, the residue of a star that detonated roughly 10,000 years prior. Upon this discovery, they recognized that its significance surpassed an alternative pulsars. The astronomers later observed in their publication in Nature that this could be a coincidence. All the evidence, location and distance, indicated its proximity to the supernova remnant. Bardet and Zwicky had surmised that the pulsar was likely the remnant of the supernova that occurred nearly 40 years earlier. Upon their subsequent observation, they adjusted the chart recorder to its maximum velocity. However, the pulses were so rapid that the pen could not distinguish them. And as the pulsar traversed the telescope's beam, they coalesced into a singular entity. They devised an innovative strategy utilizing economical yet highly effective technology to distinguish individual pulses and determine the pulsar period. They disabled the chart recorder's mechanism, allowing the paper to traverse freely beneath the pens. After removing one pen from the telescope, They connected it to the 50 Hz mains. Instead of synchronizing with the pulsar, it flickered 50 times per second on the paper, acting as an exact time reference. The other pen preserved its linkage to the telescope. Immediately before the transit, Large or Vaughan would monitor the free end of the chart recording. As the pulsar appeared in the telescope's beam, the person with the chart hurried down the corridor, dragging the paper behind them. One pen precisely documented the 50 Hz signal from the mains as a temporal reference, while the other recorded the pulsar signal, facilitating the calculation of its frequency. Utilizing this technique, they determined that the Vela pulsar emitted flashes at 11 times per second, setting a new pulsar record. The astronomers ultimately obtained a high-speed chart recorder and improved the precision of their results. A more rapid pulsar subsequently eclipsed the Vela pulsar, which had previously held the record for speed. 1 month later, astronomers employing the 300-meter Arecibo telescope in Puerto Rico reported the discovery of a pulsar exhibiting an even higher velocity near the Crab Nebula, another remnant of a supernova. We analyzed the Crab's pivotal role in the narrative of the Crab Nebula pulsar. We will now analyze the advancement of the current understanding of pulsars, supported by the discoveries associated with the Vela pulsar. In late 1968, the 64-meter Parkes radio telescope in western New South Wales concentrated on Large and Vaughan's coordinates of the Vela pulsar for additional analysis. Parkes advanced quasar research and became the foremost source of pulsar discoveries among observatories. Initially, astronomers at Parkes made significant contributions to pulsar astronomy. Haynes, Marlin, and McGee's comprehensive history of Australian astronomy, Explorers of the Southern Sky, indicates that the Cambridge announcement concerning the pulsar discovery elicited considerable enthusiasm at the radiophysics laboratory, which operated the Parkes telescope. 2 weeks later, astronomers gathered in the Parkes control room to discuss the most effective pulsar search methodology. Simultaneously, the telescope operator pursued CP 1919. Brian Robinson, a participant, recollected observing unusual movements on the pen chart recorder, the pulsarly ambiguous, prompting Robinson to increase the recorder's speed, thereby uncovering the recognizable pulse pattern. Before its substitution with polymer notes, the original Australian $50 note, composed of paper, retained the documentation of CP1919, alongside an illustration of the Parkes telescope. In March 1968, Venkataraman, Radhakrishnan, Max Komisarov, and David Cook employed the Parkes telescope to examine CP1919. They could monitor the pulsar for 4 days, contingent upon its visibility above the horizon. The fully steerable Parkes telescope was capable of tracking the pulsar's trajectory across the sky, continuously documenting the pulses, while the Cambridge group could only observe CP1919 for a restricted period each day as it passed overhead. We identified a slight discrepancy in the pulsar period compared to Hewish's reported value. The British team allegedly miscalculated the pulse count by 1, resulting in a minor temporal error of 0.00002 seconds. The Australians accurately reported the error of the Cambridge team. It is imperative to clarify the British response. However, the Cambridge group likely pursued further information. Parkes' examination of the Vela pulsar culminated in a significant revelation that elucidated the debate regarding its nature. It emits polarized radio waves. A light wave propagates through space, oscillating orthogonally to its direction of travel. In non-polarized light, such as sunlight, the vibrations propagate in all directions. However, polarization causes light to oscillate exclusively in one direction. Light reflecting off non-metallic surfaces, such as glass or water, can generate intense glare similar to sunlight reflection from vehicle windows. In December of that year, Radhakrishnan noted that the polarization angle of the radio beam from the Vela pulsar reversed with each pulse. Radhakrishnan observed that this would be rational if the beams emanated from a magnetic pole offset from the neutron star's rotational pole, as Gold and Pacini had predicted. He demonstrated that a rotating neutron star could account for the observed periods and the radio source, elucidated by a highly collapsed and concentrated magnetic field. The material, comprising a neutron star, undergoes compression and substantial collapse, intensifying its magnetic field to 1,000,000 times the strength of Earth's magnetic field. The magnetic field lines would accelerate electrically charged particles near the pulsar to relativistic speeds, approaching the speed of light as they follow their path. These particles would produce a beam of radio waves radiating from the neutron star's magnetic poles. The pulsar's magnetic poles emit a beam that traverses space akin to a lighthouse beam during its rotation. Each rotation of the neutron star would have produced a flash of radio waves if the beam had intersected Earth and its array of radio telescopes. Max Komisarov performed additional theoretical research grounded in the polar cap model theory. The notion of emissions from the magnetic poles of pulsars remains the prevailing model, despite a limited comprehension of the true mechanism behind the generation of radio beams. Gold and Pacini anticipate that as pulsars mature, their powerful radio emissions diminish due to rotational energy exhaustion. Radhakrishnan and Dick Manchester, a junior scientist at Parkes, confirmed this deceleration using the Parkes telescope. They observed a decrease of 10 nanoseconds per day by comparing the Vela pulsars period from February 1969 to that recorded in December. 2 weeks later, Radhakrishnan and Manchester employed the Parkes telescope once more to examine the Vela pulsar. They were confident in their comprehension of the pulsar and adjusted the apparatus to the predetermined pulse frequency. To their astonishment, the pulse began to recede across the screen. The pair devoted time to scrutinizing the apparatus to identify their mistake, and ultimately Radhakrishnan retired for the night, leaving the younger Manchester to rectify the problem. After observing the Vela pulsar, Manchester monitored several additional pulsars, all displaying characteristic behavior. They assured themselves that the equipment was operating correctly. However, the Vela pulsar had only accelerated by a minuscule fraction of a second. Reichley and George Downs independently identified the pulsar glitch using the 70-meter dish at the Jet Propulsion Laboratory's Goldstone tracking station. They simultaneously published articles announcing the discovery in the same issue of Nature. The glitches may result from alterations in the superfluid core of neutron stars, though scientists continue to investigate. This discovery's importance resides in examining glitches, which is one of the few methods available for scientists to study the behavior of ultra-dense matter. During the early 1970s, astronomers scrutinized the heavens for further pulsars, a quest that revealed numerous anomalous objects and phenomena, each as astonishing as the original discovery. Before the commencement of these surveys, a disorganized discovery of an additional pulsar increased its likelihood of gaining prominence in pulsar astronomy. The event began with the death of a massive star in 1054. Identifying the Crab and Vela pulsars assisted astronomers in elucidating the nature of pulsars. Nonetheless, pulsar astronomy destined the Crab pulsar to play a more prominent role. In addition to its inherent scientific value, the Crab pulsar is crucial in two significant scientific narratives. Priority, identifying the original discoverer, is a significant issue in scientific discourse. Major discoveries invariably rely on technology and, by extension, technologists, and generally build upon predecessors' contributions. Nonetheless, the credit for the discovery is attributed to the scientist who initially disseminated their research. Timely observations and precise interpretation of perceived information are essential and consistent components in this context. The discovery of pulsars is the most remarkable among the numerous narratives surrounding them. Although Bell and Hewish rightfully hold historical significance as the discoverers of pulsars, their initial detection occurred much earlier, albeit unrecognized. American astronomers detected the pulsating signal from the Crab Nebula months before Hewish and Bell's discovery with an X-ray telescope. However, the unexpected nature of the pulses resulted in an initial oversight in their observations. We will revisit that narrative later. However, it is advantageous to examine the discovery of the Crab pulsar, which transpired in two separate episodes. We acknowledge the Crab Nebula as an anomalous phenomenon. Located at the site of a supernova documented 9 centuries ago, it persisted in emitting light contrary to predictions of its demise long ago. An atypical star at the nebula's core was probably energizing this object. The southwestern star of a binary system within the nebula exhibited a vivid blue coloration and lacked the typical spectral lines associated with ordinary stars. The nebula emitted significant radio and X-ray radiation. Thus, its elevated energy output should have diminished brightness. In 1964, Tony Hewish and Samuel Okoye discovered a compact radio source that was proximate to, yet separate from, the radio emissions of the nebula. Furthermore, they indicated that the radio source displayed scintillation, implying that the entity producing the radio waves was small. The search for a pulsar in the Crab Nebula transpired within this framework. At the time of the pulsar announcement, Dave Stalin was a recently appointed Massachusetts Institute of Technology faculty member. His department head, who had instructed him at the same institution, mandated that he take a leave of absence and pursue activities elsewhere. Stalin considered the Green Bank telescope at the National Radio Astronomy Observatory in West Virginia the optimal site. What actions should Stalin undertake? Stalin sought to integrate his interests in signal processing and radio astronomy with the newly discovered pulsars, a rational selection. Upon arriving at Green Bank in June 1968, Stalin had already devised a system designed to simultaneously detect the periodicity characteristics of pulsars and a phenomenon called dispersion, like radio waves, which are also part of the electromagnetic spectrum, can disperse. As radio waves propagate through interstellar space, they engage with free electrons, causing a more pronounced delay for longer wavelengths than shorter wavelengths. Pulsars emit pulses across a range of wavelengths. Thus, as a solitary pulse propagates through space, it attenuates the longer wavelengths more than the shorter wavelengths before reaching Earth. Astronomers can determine the dispersion of a single pulse by examining the variation in arrival times at 2 different wavelengths. This evaluates the distance and proximity traversed by the pulse. In recent months, Edward Ted Reifenstein, a new hire at the National Radio Astronomy Observatory NRAO, along with engineers Bill Brundage and K.A. Briley, developed the spectrometer and the software required for signal analysis. The 91-meter Green Bank radio telescope has been equipped with the apparatus. An advanced instrument supplanted the original telescope, following its discontinuation in 1988. Like Hewish's IPS array, the original Green Bank telescope could not target any specific location in the sky. Although it was an independently mounted dish, its movement was restricted to a vertical axis along the north-south line, utilizing the Earth's rotation to scan in right ascension. Astronomers surveyed the sky by marginally altering the telescope's elevation every 24 hours.
Stalin and Reifenstein aimed to investigate the galactic plane for pulsars, as this area would presumably contain them if they were formed from supernova explosions. Supernovae transpire when massive stars deplete their life cycles. We concluded that massive stars existed for tens of millions of years and required additional time to diverge substantially from the galactic plane, where most stellar formation occurs. Although the Crab Nebula is slightly beyond their specified search area, Stalin and Reifenstein sought permission from the Telescope Time Allocation Committee to explore the region surrounding the Crab. The request has been executed. The astronomers utilized the telescope for 6 hours daily, alternating with an operator over several weeks. The astronomers recorded their observations on magnetic tape and later returned to Charlottesville, Virginia, where the Central Computer Laboratory of the National Radio Astronomy Observatory analyzed the data. At night, the astronomers employed the IBM 360 computer without budgetary limitations, predominantly delegating daytime tasks to others. The computer program was divided into two primary components: an initial filter identifying each potential combination of pulsar period and dispersion of interest, followed by a second phase that meticulously sought the most promising candidates. We assessed the candidates based on duration and variability. We examined the signals of the suspect objects across 50 different wavelengths or channels to assess their dispersion. Stalin created a threshold data plot for these potential pulsars across the 50 observed frequency channels. An asterisk or an alternative character indicates the signal strength in each of the 50 columns. Stalin recollects, "That evening, I returned with extensive printouts and was astounded to observe erratically distributed pulses across the page, spanning all 50 channels at random intervals of several seconds or more. The erratic nature of the pulses did not preclude the potential identification of a pulsar. Hewish's design of the IPS array, which can respond to swift variations in radio signals, allowed Bell to identify the first pulsar. The source appears stable if the detectors sample the signal at a frequency below the pulse rate. Stalin and Riefenstein's apparatus sampled the signal at 60 millisecond intervals, considerably shorter than the fastest known pulsar, yet the signal appeared exclusively as a random spike. In mid-October, we detected intense sudden radio signals. However, they occurred at irregular intervals, unlike the consistent timing of known pulsars. Was this a cosmic signal, or simply noise emanating from within the system? Despite lacking the typical ticks observed in other pulsars, the signal exhibited consistent peaks, resembling the selection of random giant pulses from a continuous flow of rapid pulses. This is likely a pulsar. Upon meticulous data analysis, Stalin and Riefenstein identified that two sources, NP0532 and NP0527, were in proximity in the sky. The telescope's wide beam partially overlapped the two signals. However, their distinct dispersions distinguished them, confirming to the astronomers that they had identified two pulsars instead of one. NP0532, a pulsar, was distinguished by its alignment with the Crab Nebula supernova remnant. Nevertheless, if this were a pulsar, it would further corroborate Bade and Zwicky's hypothesis regarding the connection between neutron stars and supernovae. The pulsar-supernova remnant association is highly improbable to be coincidental, thereby reinforcing the relationship between pulsars and neutron stars. Furthermore, it would corroborate Gould's prediction of a pulsar in the Crab Nebula. They pinpointed the location through subsequent observations, but required an extended sampling duration to ascertain its period. Their greatest accomplishment was setting an upper threshold of 0.25 seconds, the shortest documented interpulse interval. Stalin and Riefenstein considered preserving the confidentiality of their discovery until they could obtain additional information. Nevertheless, they promptly resolved to publish the two discoveries despite lacking knowledge of the precise periods. They believed that sharp, widely spaced pulses could solely originate from a pulsar, irrespective of the period. Nonetheless, random pulses do not define a pulsar, and the revelation of detecting even random pulses from the Crab Nebula, a remnant, prompted astronomers to respond. A group of astronomers verified the presence of a pulsar at the core of the Crab Nebula, determined its exceptional period, and precisely pinpointed its location. They achieved this by employing the Arecibo radio telescope, the largest telescope in the world. The Arecibo radio telescope is an exceptional instrument. The Arecibo radio telescope began operations in 1963 under the National Astronomy and Ionospheric Center at Cornell University. With a diameter of 305 meters, it is the largest singular radio dish on the planet. Installing such a dish in the traditional, fully adjustable manner of other telescopes is impractical. They fabricated the wire mesh dish in a natural depression in the hills of Puerto Rico, near Arecibo. It perpetually observes the sky and employs the Earth's rotation for celestial monitoring. The telescope features an extensive receiver array that spans 130 meters in length and is situated 130 meters above the dish, allowing it to focus on various sections of the dish. This allows the telescope to adjust its orientation to different positions in the sky within 20 degrees of the zenith. Notwithstanding this range limitation, one object that became visible was the Crab Nebula. In April 1968, Richard Lovelace was a graduate student at Cornell University under the mentorship of Professor Edwin Salpeter. Salpeter exhibited a strong interest in pulsars and assigned Lovelace to Arecibo for research. Other students, including David Richards, John Camella, Hal Craft, and John Sutton, accompanied him. During that period, Tommy Gold, the observatory's director, provided significant assistance to the young astronomers, although he was not the initiator of the Crab pulsar research. Frank Drake, the on-site director of the telescope, was a scientist who initiated the search for extraterrestrial intelligence, SETI, in the early 1960s. He actively advocated for the search for new pulsars. In the late 1960s, despite the presence of telescope operators at Arecibo, individuals, including graduate students, maintained complete control over all operations, encompassing telescope steering, radio receivers, and computers. Numerous equipment malfunctions were recurrent. The tropical air permeated the environment, despite the air-conditioned facility accommodating the receivers and computers. Furthermore, the electrical power in Puerto Rico was erratic, fluctuating between 55 and 65 Hz, with intermittent failures in one of the three phases of the power supply. In 1968, the analysis of radio telescope data shifted from paper chart recordings to the use of computers. Vaughan and Large utilized an unorthodox approach to augment their observations of the Vela pulsar, one of the final notable discoveries achieved without the aid of computers. Lovelace's responsibilities at Arecibo included developing computer algorithms for pulsar detection using the observatory's CDC 3200 computer and analyzing the telescope's data for pulsar signals. In October, he created a novel computer algorithm to detect weak periodic signals within radio interference. What was notable about our work at that time was our prediction of relatively high frequencies, 50 Hz, linked to rapidly rotating pulsars, Lovelace recalls. At that time, many scientists posited that the objects were white dwarfs, capable of emitting only low frequencies, approximately 1 Hz. During one of Tommy Gold's visits to the observatory in October, Lovelace recalls that Tommy passionately implored him to investigate the high frequencies expected from rotating neutron stars. Lovelace designated his new program Gallop due to its exceptional velocity in performing Fourier transforms on large data samples approximately 16,000 in length. Lovelace had access to the computer from midnight to 8 a.m. on weekdays and all day on weekends. On the night of November 9th/10th, 1968, he calculated the initial 4 digits of the Crab pulsar's period, 33.09 milliseconds. David Richards markedly increased the duration, noting that it gradually extended. David Richards first localized the Crab pulsar by allowing it to move through the telescope's field of view and measuring its intensity at 195 MHz using the Gallup code. About 1 week later, observations at 430 MHz precisely established the pulsar's location within 5 arc minutes of the Crab Nebula's center. This accuracy is crucial for the ensuing optical discovery. The colossal pulses were crucial for identifying the Crab pulsar and other short-period pulsars. Dave Stalin conveyed that others had similarly examined the Crab, searching for periodic pulsar emissions. However, most instruments necessitated more rapid sampling or computational support to identify fleeting intervals. The giant pulse phenomenon, defined by the Crab's intensely emitted pulses alternating with significantly weaker emissions lasting several seconds or more, was crucial to our success. Nonetheless, these substantial pulses are challenging to detect manually or through alternative methods due to their infrequent occurrence and lack of repetition. The recurrent dispersion was the distinguishing characteristic of these giant pulses. Without substantial emissions from the Crab pulsar, radio astronomers may not have recognized pulsars with exceptionally short periods. No comprehensive radio surveys conducted in the following 16 years would have detected the Crab or Crab-Other pulsar within such a short duration. Astronomers utilizing various wavelengths, particularly optical and X-ray, probably captured observations with sufficient temporal resolution to accurately identify the Crab. The Crab pulsar was the first detected in visible light, a narrative fraught with disputes over precedence. Before leaving the Crab pulsar, we shall investigate how the revelation of the initial radio pulsars led to the realization that pulsars had been previously detected but unacknowledged before their discovery. 1 month before Jocelyn Bell's seminal observations leading to the discovery of pulsars, a young American graduate student, Jerry Fishman, scrutinized the pristine pre-dawn sky above Palestine, Texas. A balloon with a diameter of 130 meters, equipped with a distinctive astronomical instrument, ascended above him. Unlike radio or optical telescopes, this instrument is capable of observing the universe in gamma rays and X-rays, two types of high-energy radiation that correspond to some of the most powerful phenomena in the universe. The problem is that Earth's atmosphere diminishes Y-rays and X-rays. While beneficial, it obstructs our capacity to observe the high-energy universe. To achieve that, one must rise beyond the atmosphere. Although being suspended beneath a balloon may appear an improbable sight for a telescope, it was the most feasible alternative to utilizing space-based instruments. Fishman and his colleagues devoted most of the night to preparing the balloon for a pre-dawn launch, ensuring that the telescope was situated at a high altitude to observe the Crab Nebula that day. Fishman recalls the surreal imagery created by the balloon's extraordinary altitude, surpassing 50 stories, the jet engine-like noise during helium inflation, and the vast launch pad that accompanied the specialized large launch vehicle. This vehicle can transport the gondola, maneuver, and adjust to abrupt changes in wind direction. Local inhabitants and reporters consistently engaged in balloon launches. During our launch, friends and colleagues from Houston journeyed 4 hours to Palestine. Fishman noted the balloon's ascent to approximately 40 kilometers above the Earth's surface, with 99.5% of the atmosphere beneath it. The remote control instructed the telescope to rotate and focus on its Crab Nebula target. In 1965, Fishman initiated his graduate studies in the newly formed Department of Space Science at Rice University in Houston, Texas, and began exploring the diverse research specialties within the domain of space science. One of these fields was gamma-ray astronomy. He visited the library to obtain additional knowledge about the field, but found only a limited selection of literature available. Capitalizing on the opportunity to engage in an emerging and potentially exhilarating discipline, Fishman joined Robert C. Hames's gamma-ray astronomy group in the summer preceding the commencement of classes. The Rice University group was among the select few globally conducting balloon-borne observations of high-energy phenomena. 2 supplementary research teams were from MIT, headed by George Clark, and the University of California, San Diego, overseen by Lawrence Peterson. The 3 groups engaged in fierce competition to be the first to identify radiation and analyze the spectra from diverse, high-energy objects. The Crab Nebula was an unequivocal target, an established radio and visible radiation source. In 1964, Herbert Friedman from the Naval Research Laboratory demonstrated that the Crab Nebula originated low-energy X-rays. It was the inaugural discrete X-ray source to be recognized. He employed the identical lunar occultation technique utilized by Parkes to discover quasar 3 C273. Several years ago, Palestine operated a permanent scientific balloon flight facility. Universities in the United States and internationally employed the facility to perform scientific balloon flight experiments for various atmospheric and astronomical investigations. The personnel guaranteed Fishman and his colleagues preferential treatment as the exclusive Texas institution utilizing the facility. Nonetheless, they ultimately found this assurance to be untrue. Telescopes designed for high-energy universe observation fundamentally differ from optical or radio telescopes, which employ a reflector to gather and focus light or radio waves for detection. Despite the absence of focusing capability in ordinary light compared to gamma rays, detection is still achievable. The device would consist of a detector within a box featuring an aperture for the passage of Y-rays. We can ascertain the X-ray source by analyzing the detector's orientation without acquiring an image. However, monitoring the gamma-ray sky poses significant challenges. X-rays can penetrate the telescope casing, creating a haze obscuring the examination subject. For the astronomers, it was comparable to trying to take a standard photograph with a transparent camera. Even LEED, which effectively attenuates harmful gamma rays and X-rays, proved insufficient for their protection. Cosmic rays, a continuous influx of high-energy particles from space, would generate gamma rays within the LEED, emitting radiation at gamma-ray wavelengths and obscuring the visibility of the events occurring. We outfitted the Y-ray telescope with 2 overlapping detectors to resolve these concerns. This configuration necessitated both detectors to identify the gamma rays emitted by the observed object for documentation purposes. We deployed a reliable detector, and the configuration of the Y-ray detectors created a direct line of sight to the source. A mechanized drive system stabilized the instrument, observing the target as the balloon navigated the sky. The comprehensive detector system represented the largest gamma-ray detector ever built for balloon or spaceflight observations, and it was indisputably the most expensive and heaviest element of the telescope. The gondola that supports the telescope has a mass of approximately 600 kilograms. The balloon was launched shortly after 6 in the morning, reached its maximum altitude 3 hours later, and began observations. The telescope pivoted as instructed and focused on the Crab Nebula. This transpired in June 1967. Fishman and his colleagues knew Baade and Zwicky's assertion that the Crab Nebula would contain a neutron star. Upon inquiry, Hames directed them to dismiss the concept. He claimed that unconventional theorists had suggested the unsubstantiated notion of neutron stars. The balloon flight was successful, enabling us to measure the energy spectrum of the crab for the first time, resulting in an energy of several hundred kilo-electron volts. The team took pride in their accomplishment. The resulting paper established the Rice University Group as a leader in this field. A consortium of British radio astronomers subsequently declared the discovery of several pulsating radio sources. The Rice Group was oblivious to any correlation between pulsars and their high-energy observations. However, upon receiving the information, Fishman recognized the potential presence of detectable X-ray or gamma-ray pulses emanating from the Crab Nebula. He was composing his thesis, which entailed quantifying high-energy radiation from extragalactic sources. A distinguished theorist at Rice discouraged Fishman from analyzing the 1967 balloon flight data for signs of a pulsing signal. A distinguished theorist at Rice cautioned Fishman that he would waste his time and should focus on his thesis instead. Despite this discouragement, I decided to employ our Crab Nebula flight data from June 1967 to examine pulsations from the Crab, Fishman recalls. In late 1968, Stalin and Riefenstein announced their discovery of the Crab pulsar. The Naval Research Laboratory, NRL, X-ray rocket group's discovery of low-energy X-ray pulses from the Crab pulsar during rocket flight observations further inspired Fishman. A succession of fortunate occurrences aided his pursuit of pulses. The detector's comprehensive shielding resulted in a low counting rate, enabling the simultaneous recording of individual X-rays and gamma rays upon detection. If we had gathered and recorded the X-rays and Y-rays, we would not have had adequate temporal resolution to detect the rapid pulses from the Crab Nebula. A multi-track tape recorder documented the data throughout the balloon flight, incorporating precise timing information from the radio station WWV on a simultaneous track. Rick Harnden, a graduate student and computer specialist, skillfully programmed a significant computer to integrate the Crab Nebula observations from the 1967 balloon flight, potentially revealing a detectable weak signal from the Crab pulsar. The process entailed the continuous folding of the data at the pulsar period of roughly 33 milliseconds throughout the recording. The problem was that the Crab Nebula required adequate constancy of its pulse period. Fishman and Harnden asserted that folding the data at a time different from that of the Crab pulsar over an observational duration exceeding 3 hours could conceal the pulses, irrespective of their presence. The first step involved converting the analog tapes from the balloon flight, recorded in Palestine and at a downwind telemetry receiving station, into a digital format, a process that had not yet been executed. Instead of consolidating data over separate time intervals for the source and background, usually approximately 10 minutes each, they were mandated to preserve the data as discrete, identifiable, time-stamped photons. The data will comprise individually identified X-ray and gamma-ray photons, time-stamped with the WWV signal on the analog tape to an absolute precision of approximately 1 millisecond. After convincing the director of the computer facility at Rice of the viability of their research project, Fishman and Harnden were granted access to the main campus computer for several overnight sessions to analyze various trial periods within the entire database and determine the correct one. This facilitated the search. In the 1960s, this task required substantial computational resources, necessitating several nights of computer operation. Ultimately, they attained the accurate period, resulting in a significant pulsar signal. The pulsar's signature had been evident in the data months before Bell's discovery, had they merely comprehended what to pursue and how to analyze it. Fishman and Harnden were keen to present their discoveries to the scientific community and the general public. The International Astronomical Union circulars, a communication system, sent a telegram to astronomers worldwide. The Public Relations Office at Rice University promptly organized a press conference that week in the department's spacious lecture hall for local journalists and representatives from national publications. A former World Book Science Service correspondent wrote a comprehensive feature article on the discovery, highlighting the contributions of graduate students Fishman and Harnden, along with a photograph of the pair. Many distinguished newspapers in the United States and internationally disseminated this article, as evidenced by the clipping service employed by the Rice PR office during that period. The young scientists achieved immediate notoriety, receiving calls from colleagues, friends, and family who had seen the article and their images in the local newspapers. They composed and submitted the scientific details of the observations to the Astrophysical Journal letters within a week. Harnden submitted the manuscript to Subramanian Chandrasekhar, the University of Chicago press editor. He was impressed by the revelation that Harnden had personally conveyed the manuscript from Houston to Chicago. He was oblivious that Harnden's father was a pilot for Braniff Airways, allowing Rick to fly anywhere within their network free of charge. We will analyze the circumstances related to the discovery of the first optical pulsar, the Crab pulsar, which sporadically emits visible light. However, we must first examine its significance. Philip Morrison asserted that the Crab Nebula and its pulsar serve as a Rosetta Stone for high-energy astrophysics. These entities encompass concepts related to the formation of neutron stars and supernova remnants stemming from the recorded supernova explosion in 1054 AD. Furthermore, we can analyze the nebula and the pulsar over 18 decades of energy, ranging from the radio spectrum to gamma-ray energies. Many observational and theoretical studies have been published concerning the Crab Nebula and its pulsar. Many books, scientific conferences, and workshops have focused on the relationships between these two entities and broader astrophysical domains. These two objects have been a favored focus of inquiry for almost all space-based telescopes. Composite HST and Chandra X-ray images and videos provide compelling visuals of the nebula and the filaments of matter emitted from the pulsar into the nebula. Before 1969, the persistent energy output of the Crab Nebula, nearly 1,000 years after its explosion, was perplexing. The pulsar reliably emits energy into the nebula and beyond via high-energy particles and waves. In the late 1940s and early 1960s, scientists recognized the Crab Nebula as one of the first radio objects in the galaxy and the X-ray spectrum. However, they only identified its pulsed radio emission after discovering several other radio pulsars. This was chiefly an observational challenge. Detecting rapid radio pulsars necessitated substantial effort. We consistently identify pulsars in radio and optical wavelengths with millisecond periods. The Crab pulsar is a faint star within the considerably brighter surrounding nebula at visible wavelengths. At X-ray wavelengths, it becomes more pronounced, and at even higher energies, the pulsar completely eclipses the emission from the nebula. A newly established ground-based Hess gamma-ray observatory in Africa has recently observed the Crab Nebula at TeV energies. The Crab pulsar is unobservable at these energy levels, and the pulsed emission comprises less than a few % of the nebula's flux. The three astronomers scrutinized the screen, reflecting heightened anticipation and lowered expectations. Two of them were theoretical astronomers who acquired their initial practical experience at an astronomical observatory. Despite the playful remarks from experienced observers about their access to a telescope, the pair secured time on a relatively small, nearly obsolete telescope that had seen better days. They obtained the support of an experienced observational astronomer who had developed much of the equipment. While their primary aim was to gain observational experience, the theoretical astronomers concentrated on a significant topic in astronomy at that time: the enigmatic optical pulsar. Experienced observers endeavored and failed to detect optical pulsars. Consequently, they searched with limited optimism for unique flashes of light associated with the recently identified Crab pulsar, indicating that pulsars emitted visible light and radio waves. This discovery would be consequential, considering its ramifications for understanding pulsars. The success indicator would be a distinctly delineated curved line of green dots running through the center of the display. On that frigid winter evening in 1969, the astronomers observed the screen in darkness and anticipation. The question remained during the New York conference: is it possible to observe pulsars in visible light or the optical spectrum? Rapid radio pulses indicated that pulsars are compact objects. However, radio telescopes lacked the resolution to precisely ascertain the exact location of the pulses in the sky. Optical telescopes can reveal their true characteristics by studying pulsars at wavelengths exceeding radio. Detecting a pulsar at optical wavelengths would indicate a significant increase in energy output, as illumination at optical wavelengths requires considerably more energy than at radio wavelengths. Thus, A notable accomplishment in astronomy was identifying a visible object associated with radio pulsars. Locating an optical counterpart for any known pulsar has been challenging due to inadequate resolution at radio wavelengths. Hewish and his colleagues observed from the beginning that the positional accuracy of the IPS array, while facilitating the discovery of CP1919, required enhancement for any significant identification of the responsible star. The search area adjacent to the galactic plane includes 2 stars of 12th magnitude and several fainter objects, as indicated in the original paper. A preliminary hypothesis is the sole explanation for these extraordinary sources without supplementary data. Nevertheless, multiple astronomers pursued its identification, and 2 teams proclaimed their discovery of the elusive optical pulsar at the conference. This account of the conference week in January 1969 is based on literature and participants' recollections in one of the most thrilling narratives of pulsar astronomy. Al Cameron, the scientific organizer of the New York conference, had extensively authored theoretical papers on the properties of neutron stars, including their vibrational frequencies. Steve Marin, one of his graduate students, often ridiculed Cameron for publishing multiple papers on a purely theoretical construct at that time. One day Marin was crossing the Sonoran Desert from Tucson to Kitt Peak Observatory when the radio reported that British astronomers had detected pulsating radio sources from deep space. The British scientists claimed that these were the long-expected neutron stars. During the 1960s, the lack of mobile phones necessitated Marin's wait until his arrival at Kitt Peak Observatory to communicate with Cameron, extending congratulations on the discovery of neutron stars and expressing remorse for previous jesting. Cameron replied, "Thank you, Steve, but there has been no success thus far. These cannot be neutron stars due to the inadequate vibration rates, according to Cameron's interpretation of the pulse rates." The subsequent day, Cameron reached out to Marin at Kitt Peak and conveyed his conviction that the recently identified pulsars were, in fact, white dwarfs oscillating at unexpectedly elevated frequencies. This requires minor modifications to the white dwarf theory. However, Marin should direct the chief observer at Kitt Peak, Roger Linz, to investigate optical pulses. Marin traversed the corridor to Linz's office and conveyed the message. Within an hour, Linz contacted Marin and reported that he had devised a method to search for the optical pulses. The issue arose from his requirement for immediate access to the telescopes. Marin owned a telescope solely for his personal use. During that period, the 1.3-meter telescope at Kitt Peak operated as an experimental, remotely controlled device to which Marin had sole access. Linz suggested that if Marin provided the telescope, he would supply the instrumentation, allowing them to collaboratively search for optical pulses emitted by white dwarfs. Linz acquired the necessary equipment in collaboration with Donald Trumbo, the director of electronics at Kitt Peak. The astronomers aimed the 1.3-meter telescope at CP1919, seeking evidence of optical pulses. Collecting the light from the pulsar and measuring its intensity at a fraction of the radio pulse period to detect optical pulses was imperative. The procedure entailed affixing a photometer that transforms light, gathered by a telescope, into an electrical signal. They subsequently measured the signal's intensity by observing variations in light intensity, which indicate optical flashes aligned with the radio pulses. They initially achieved success and announced the discovery at the New York conference. The variation in luminosity was negligible, only 4% of the star's mean brightness, and it oscillated at twice the frequency of the radio pulsations, which was certainly not coincidental. The theorists deemed the concept perplexing, inquiring what could prompt the optical pulses to appear with each alternate pulsar rotation. The following day, a weary astronomer, David Kudabak, arrived from Lick Observatory, where he had been examining CP1919. confirmed the optical pulses and recorded an unexpected variation in the pulse period, fluctuating by as much as 10% in both acceleration and deceleration. Q-back detected optical pulses, albeit in an unexpected manner. Unfortunately, subsequent observations from multiple observatories in the following months did not validate either set of results. The claims about detecting optical pulses from CP 1919 were premature, and the reasoning remains unclear. Marin and Linz endeavored to locate the 3 remaining pulsars that had been previously announced, but their efforts were futile. Marin and Linz ultimately agreed to cease their pursuit of optical pulses, which led to the unused assembled equipment. Optical pulses emitted by pulsars have remained undetectable. Within 6 weeks of the announcement of Hewish and Bell's discovery, astronomers at Cambridge were simultaneously examining optical pulses from CP 1919 that corresponded with the radio pulses. On April 5th and 6th, 1968, Roderick Willstrop and John Jelly conducted observations with the 0.9-meter telescope at the Institute of Astronomy. Yet they observed no optical flashes from CP 1919. The discovery of pulsars exhibiting variable pulse rates required a more versatile recording method and an improved photometer, as the current apparatus was restricted to detecting a singular pulse frequency at any specific time. To accelerate and improve the assessment of the color of the studied objects, Willstrop developed a photometer featuring a wheel with 4 filters in the telescope beam. Concurrently, Ed Kibblewhite devised and assembled a photometric recording device featuring a high-velocity punch to capture the photometer's output. The latter could perforate 7-track paper tapes at 110 rows per second. The paper tape was allowed to descend, or the term pew was more appropriate when the punch functioned near its maximum capacity into a wooden box, a tea chest approximately 60 cubic centimeters. After each observation, we finalized the tape utilizing a modified manual grinding wheel, conveyed it to the Cambridge University Computer Laboratory, and analyzed it for periodicities. The origins of the radio pulsations were twofold: white dwarfs or neutron stars. The identification of the Vela pulsar by Vaughan and Large in Nature did not eliminate white dwarfs as the most likely candidates for pulsars. The December Science issue subsequently reported the discovery of the Crab pulsar by Stalin and Riefenstein. The discoveries were deliberate, identifying 2 high-velocity pulsars linked to supernova remnants significantly validated Baden-Zwicky's prediction from nearly 30 years earlier. Pulsars are required to be neutron stars rather than white dwarfs. Willstrop had previously obtained time on the 0.9-meter telescope and intended to employ the new photometer to examine white dwarf stars and exclude them as potential sources of optical pulses. Overcast conditions on November 23, 1968, prompted Willstrop to withdraw at 9:30 p.m. Nevertheless, the sky cleared an hour later, and he continued to observe. Willstrop conducted additional observations that night and again in the early hours of the 25th, devoting further time to studying white dwarfs throughout the week. Willstrop conveyed the gathered paper tapes containing data from the white dwarf observations and the alleged neutron star at the center of the Crab Nebula to the computer laboratory for analysis, 1 or 2 at a time. The date was December 1968. In August of that year, 2 young theoretical astronomers from different sides of the Atlantic arrived in Tucson, Arizona, unaware of their common destination, Steward Observatory. The University of Arizona in Tucson administers this observatory, which features its principal telescopes on Kitt Peak. John Koch was an American astronomer connected to the NASA Goddard Institute for Space Studies, whereas Michael Disney was a British astronomer linked to the University of London Observatory, Mill Hill. They fortuitously met at the poolside of a motel where they and their spouses had obtained temporary lodgings while seeking a permanent residence. They commenced a dialogue and ascertained they were heading to the same observatory. Notwithstanding his theoretical background in astronomy, Disney felt overwhelmed by numerous experienced telescope users. He later admitted that he was unaware of what a telescope looked like. Given their inexperience, the two astronomers determined it prudent to mitigate the situation by reserving telescope time and making observations. Cocchi and Disney were surprised when they requested telescope time and were allocated several nights on a modest 90-centimeter telescope. The observatory administrators assumed the pair would only waste a few nights, considering it a minor loss for the observatory. Notwithstanding its historical importance, the telescope had arrived at the end of its operational lifespan. Telescopes are claimed to have a functional lifespan of around 50 years. They do not inherently degrade, but technological advancements make their size and sensitivity obsolete. Based on that criterion, when Koch and Disney entered the dome-shaped structure in 1922, the 0.9-meter telescope was already obsolete. The telescope was originally built on the University of Arizona campus in Tucson and was the first to be fabricated using American-made materials. The city's growth brightened the surroundings, requiring the relocation of the obsolete telescope to the darker skies of Kitt Peak in 1962. Substantially larger instruments now eclipse the telescope. Nonetheless, the existence of Kitt Peak Observatory is partially due to the 0.9-meter telescope. The indigenous people revere the mountain on their reservation. While in Tucson, the 0.9-meter telescope enabled the Tribal Council to approve telescopes on Kitt Peak by offering a celestial viewpoint. Upon the arrival of Cook and Disney, the telescope was perceived as small and obsolete. Upon obtaining telescope time, what should Koch and Disney prioritize for their observations? Despite acknowledging the minimal likelihood of success, they pursued the search for pulsars within the optical spectrum. Cocchi consulted multiple esteemed astrophysicists about the possibility of detecting a pulsar at visible wavelengths. However, they all conveyed skepticism and cautioned him that it would be in vain. All agreed that pulsars would be too distant and faint to be observed at optical wavelengths, due to the considerably higher energy required for an object to emit visible light than radio wavelengths. Furthermore, additional, more experienced observers have been seeking optical pulses since May without success. Nonetheless, the aim was to gain experience with telescopes. Koch and Disney felt they had nothing to lose. Where should one conduct a search? Given that the resolution of radio telescopes is significantly lower than that of optical telescopes, the coordinates of the detected pulsars could have been more precise. The discoveries of the Vela and Crab pulsars transformed the field by associating a radio source with an optical counterpart, namely a supernova remnant. The Vela supernova remnant is a vast, intricate filament spanning the sky, while the Crab nebula is considerably more compact, with a diameter roughly 1/5 that of the full moon. The arrogant Lovelace and his colleagues accurately identified the position of the Crab pulsar within 5 arc-minutes of the nebula's center. If the pulsar is the remnant of the star that produced the Crab supernova, the most rational site for investigation would be the center of the Crab nebula. In 1942, Bade and Minkowski identified Bade's star as the likely remnant of the supernova, distinguishing it from the other stars at the center of the Crab nebula. While other stars are detected within the nebula, Koch and Disney chose to ascertain whether Bade's star pulsated optically at the radio source's identical frequency. Identifying an optical pulsar is more complex than simply observing through a telescope or using electronic devices to relay an image to a screen and watch for a flickering light. If the suspected pulsar emitted flashes at the same frequency as the radio pulses, which for the Crab pulsar occurs every 0.033 seconds, the human eye would perceive only a continuous illumination due to its slower response. Cocchi and Disney necessitated an alternative methodology for pulse detection, requiring specialized equipment and expertise. Ray Wayman, an astronomer at Steward Observatory, suggested consulting another astronomer associated with the observatory. The astronomer was Don Taylor. Taylor is an electronics specialist involved in a project examining the potential existence of underlying galaxies and quasars. He utilized a technique known as area scanning to achieve this. He attached a device with a narrow aperture to the telescope precisely where the image appeared. Laterally moving the slit across the field of view caused variations in the light intensity transmitted through the slit as it passed over the observed object. When the slit, the transmitted light intensity varied, producing a light curve, a graphical depiction of light intensity about position within the field of view. Owing to the dimness of quasars observed from Earth, Taylor required prolonged observation of a specific quasar to collect sufficient light for thorough analysis. This concern prompted him to create a device specifically designed for pulsar detection. The Earth's atmosphere continually modifies and distorts the light from celestial bodies, making a single slow scan noisy and distorted. A rapid scan typically produces enhanced accuracy, similar to taking a brief exposure photograph of a moving object. However, it allows less light to enter the aperture, resulting in a reduced signal. We can improve the clarity of the light curve by consolidating signals from several brief scans and computing an average. We performed this averaging on a specialized computer called a CAT, which denotes Computer of Average Transients. The CAT consolidated each scan to produce an average curve depicting the variations in the quasar's luminosity throughout its range. This became the optimal solution for Koch and Disney. The anticipated optical pulses from a pulsar would appear as intermittent, faint, and irregular light curves. Each activation and deactivation of the pulsar would cause its luminosity to vary, producing a light curve for each unique optical pulse. The telescope captures light from a pulsar, whose intensity varies by its sporadic radio emissions. The CATI could sample light at the designated frequency and subsequently integrate the individual light curves from multiple pulses, displaying them as a unified curve. How can we instruct the CAT to sample at the designated pulse interval? During area scanning, the telescope alerts the CAT before initiating each scan, enabling it to confirm the commencement of each light curve. In the optical pulsar search, the CAT requires a frequency synthesizer to determine the initiation of each curve. Radio astronomers could align this device with the observed pulsar. Its purpose is to instruct the CAT on the appropriate sampling rate for the data, indicating the initiation of each light curve. Despite Taylor's requirement for additional equipment, an unused item was serendipitously discovered on the same mountain from a prior attempt to find the elusive optical pulsar. John Koch had never met Moran or Linz, but crossed the short distance from his office at Steward Observatory to the Kitt Peak National Observatory headquarters across Cherry Avenue. He notified Moran of his status as a theoretical astronomer, expressing his suspicion that the fastest pulsars would produce the most radiant pulses. Koch indicated that he and Disney intended to investigate optical pulses from the recently discovered, and undoubtedly swift, Crab pulsar. Can Moran provide any equipment? Moran and Linz had previously established that the origin of the optical pulses was less luminous than any phenomena observed by astronomers at that time. They employed a 1.3-meter telescope and consolidated their observations over several nights, allowing them to electronically reduce background light and improve the contrast between the pulsar signal and the ambient sky. All their efforts had been in vain. Marin and Linz, based on their experience, regarded the quest for optical pulses from the Crab as trivial. Nonetheless, they provided Koch with their frequency synthesizer and an auxiliary device, a pulse amplifier. This apparatus, attached to the telescope, identifies individual photons of light and transforms them into electrical signals for the CAT to document and examine. They necessitated an extra apparatus, a photometer. Koch, Disney, and Taylor acquired one from Walt Fitch, a colleague astronomer at the Steward Observatory. Fitch and other astronomers specifically engineered the Fitch photometer for use with the 0.9-meter telescope. Having obtained the equipment and telescope, they necessitated experience. Friday, January 10, 1969. The 0.9-meter telescope employed a Newtonian design, which is common in amateur telescopes, but rare in professional ones. The astronomers ascended a gantry above the observatory dome to install equipment, as the telescope's observational apparatus is situated high when aimed at the night sky. We ensured total darkness within the dome to enable the telescope and its detector to detect the faint signals from the pulsar. The extreme cold of Kitt Peak in winter exacerbated the situation, and Disney, unprepared for this, wore only a sports jacket. The absence of a safety railing on the gantry and the extreme cold significantly increased the risk of a severe fall, presenting a considerable obstacle to the commencement of observational astronomy. Disney began to reflect on his existential purpose. Taylor and night assistant Bob McAllister established and oversaw the electronics, while Koch and Disney developed expertise in employing the telescope to detect pulsar candidates. In the obscurity and cold, they discerned nothing. Subsequently, the clouds enveloped the sky, marking the conclusion of Koch and Disney's first night employing a telescope. Koch, Disney, and Taylor returned to the telescope the following night to undertake their first significant detection effort. Despite the equipment and telescope functioning flawlessly, no observations were conducted. The third night of their significant observation period passed without incident or result. The weather worsened, hindering their last 2 nights at the telescope and leading to a deficiency in observations. Thereafter, fate intervened. Bill Tift, the astronomer designated to operate the telescope, reported that his wife had become ill, preventing him from using it. Would Koch and Disney value the extra 2 nights of observation time? They promptly accepted the proposal. Taylor returned to the Tucson University campus to be available to his students as they prepared for examinations. He determined that his presence was superfluous, given that the electronics had been installed and were operating effectively. Furthermore, they necessitated a larger telescope and had obtained time on the Lunar and Planetary Laboratory's 1.6-meter telescope for the evenings of February 15th and 16th. Taylor did not perceive an immediate need to remain, given the likelihood of additional negative outcomes with the 0.9-meter telescope. McAllister remained to aid the 2 astronomers. While awaiting clarification from the sky, Koch chose to reevaluate his calculations. During dinner, they discussed the project, during which Koch remarked that Earth orbits the Sun, sometimes nearing the pulsar and at other times moving away from it. It is akin to witnessing a friend beside a carousel as you walk past. The Doppler effect demonstrated that the pulsar's frequency would increase as Earth approached it and decrease as it moved away. They subsequently acknowledged their mistake in calculating the pulsar period. They had been analyzing the erroneous period. Koch felt foolish for misjudging the correction for Earth's motion. Despite this and the project's ineffectiveness, Koch diligently re-examined all the calculations. Koch, Disney, and McAllister went to the dome that evening to recalibrate the timing apparatus. Upon configuring the telescope, it functioned as expected. The astronomers aimed the 0.9-meter telescope at the center of the Crab Nebula. The 3 individuals knelt before the monitor. A proliferation of green dots appeared in the center of the monitor almost instantaneously. The trio stared in disbelief at the monitor. Disney has officially announced, "We have a vital sign here." The monitor exhibited a waveform demonstrating that the telescope precisely identified optical flashes in synchrony with the radio pulsar in the Crab Nebula. Koch stated, I expect it will be a historic moment. We will determine the results after performing a second reading. If that spike is once more situated centrally, the spike is positioned centrally, which raises my apprehension. A combination of enthusiasm, skepticism, and disbelief surrounded them as they examined possible sources of error. They deactivated the equipment and restarted it to eradicate the potential for an electronic artifact. The pulses reappeared. "My God, it persists," Disney stated. "It is as remarkable as before, if not better than the prior instance." The trio was almost ecstatic, but briefly restored their composure. Koch ultimately suggested redirecting the telescope from the crab to determine if the signal discontinued. It transpired, though not completely. A faint pulse remained evident despite the telescope's misalignment with either star. Consequently, they modified the computer's frequency to remove the equipment as the pulse source. Adjusting the frequency resulted in the signal's disappearance, confirming that the detected pulses did not originate from the electronics. Disney subsequently proposed that the telescope might not have been adequately distanced from the nebula, leading to a slight influx of light from the pulsating star into the telescope. To negate this possibility, they realigned the telescope to examine a completely distinct area of the Crab Nebula. The pulses disappeared entirely. They returned to the Crab, where the pulsar was periodically illuminated and extinguished. Koch and Disney unequivocally identified the first optical pulsar. Disney regretted Don Taylor's absence during the discovery, highlighting his substantial contributions to its facilitation. Disney reached out to him. "Don, we have identified the pulsar." He clarified the temporal inconsistency to Taylor and the actions implemented to address it, yet Taylor remained unconvinced. "The inaccurate detections increased my awareness of avoiding a similar mistake," he recalled. Taylor posited several hypotheses concerning the characteristics of the pulses aside from the pulsar itself. Taylor instructed Koch and Disney to conduct standard tests by repositioning the telescope away from the pulsar and adjusting the cat sweep period to determine if the pulse remained detectable. The observation was valid. However, he directed Disney to uphold confidentiality concerning the discovery until he could conduct an additional telescope run for verification. Taylor conveyed concern about a potential technical failure and the possibility of other astronomers employing more advanced telescopes to appropriate the discovery. He was prepared to drive to the observatory that night. However, Disney recommended silence as the clouds were once again approaching. After Disney ended the phone call, the trio at the observatory devoted the rest of the night to repeating the observation using different colored filters and making further adjustments to the experiment. The following evening, the last night at the telescope, was clear. The observation was restructured for Taylor, who conducted multiple tests to confirm that the electronics were not providing misleading information. Taylor swiftly communicated his colleagues' conviction. They had observed optical pulsations emanating from a pulsar. Nonetheless, a lingering question persisted. Which star comprised the pulsar? The Crab Nebula houses two central stars, either of which could have caused the pulsations. Astronomers distinguish between proximate stars by denoting their relative positions as north or south, and indicating which star precedes or follows the other. The latter part of the description stems from the observation that, when observing through a stationary telescope, objects seem to move across the field of view from east to west, similar to participants in a parade. The Earth's rotation causes the telescope to appear to move east-west. When observing through the telescope, objects to the west advance ahead of those to the east, which trail behind. We labeled the two stars at the core of the Crab Nebula as preceding and north following. Although their apparent brightness is similar, Walter Baade dismissed the north following star as the energy source for the Crab Nebula in 1942. Since then, individuals have generally not perceived the north-following star as physically associated with the Crab Nebula. We recorded the observations on audio tape for convenience during the observation sessions. We unintentionally permitted the tape to persist in recording, leading to an unedited account of the events as they unfolded, explicitly state their conviction that the identified pulsar was the south preceding star. Despite the widespread skepticism about identifying the north-following star as the pulsar, Koch, Disney, and Taylor sought to verify its legitimacy. Astronomers require the ability to distinguish the light from one star and then another to identify the optical pulsar via its pulses. The difficulty for Koch, Disney, and Taylor was that the two stars were nearby within the telescope's field of view. They necessitated a diaphragm, a narrow metal plate with a tiny drilled aperture, to observe a solitary star, sufficiently diminutive to obscure all but the intended star. The diaphragms utilized on the 0.9-meter telescope until that point were overly large, allowing light from both stars to concurrently enter the photometer. Understanding the negligible distance in the sky they faced is crucial to comprehend their challenges. Distances between celestial objects are expressed in degrees, minutes, 1 degree equals 60 minutes, or 60 inches, and seconds, 1 minute equals 60 seconds, or 60 inches. The Moon has an approximate diameter of half a degree. In contrast, the star Alpha Centauri, consisting of two stars located less than 18 inches apart, can be easily seen as two separate stars through a small telescope. However, the separation of the double star in the Crab is considerably smaller, at only 4 inches. Thus, the light from each star requires a diaphragm of equal or smaller diameter. The diaphragm utilized by Koch, Disney, and Taylor had a diameter of 22 inches, which was excessively large for precise pulsar identification. Thus, they sought an alternative approach. Upon verifying the optical pulses for Taylor, the trio accurately determined the likely location of the pulsation source by systematically adjusting the telescope away from the Crab Nebula's center and observing the distance until the pulsations terminated. Utilizing this astronomical analogy of searching in obscurity, they were able to propose in their IAU circular. The pulsar is estimated to be located 5 arcseconds north and 4 arcseconds east of the southern preceding star of the Crab central double. We estimate the positional error to be approximately 5 inches. This placed the likely source of the optical pulsations frustratingly close to the location of the north-following star, including the south preceding star. Scientific principles required them to document their observations rather than speculations, despite the prevalent skepticism regarding the north-following star being the pulsar. In their subsequent publication in Nature, the three tentatively identified the pulsar as the south preceding star. They necessitated a larger telescope and/or a smaller diaphragm to sequentially isolate each star and identify the authentic pulsar. The participants' testimonies exhibit significant inconsistencies at this point in the narrative. A dialogue transpired between Koch and Linz concerning the potential for the three new astronomers, alongside Marin and Linz, to employ a larger 2.1-meter telescope to identify the pulse-emitting star. However, after several years, Iho proposed and rejected the suggestion. Remains undetermined. The concept ultimately proved unsuccessful. The discovery announcement was clearly public, inciting an immediate race to determine the source of the optical pulses. Marin and Linz could have devoted additional time to hunting had they discerned which of the two Crab stars was the pulsar. The 2.1-meter telescope could produce larger images than the 0.9-meter telescope employed by Koch, Disney, and Taylor, and it included diaphragms as small as 1 inch in diameter. Given the situation, they considered it unwise to retrieve their equipment. Therefore, they constructed the necessary electronics and prepared the 2.1-meter telescope for the evening's observation. Currently, 2 teams on the mountain are investigating the definitive source of the optical pulsations. Due to the limitations of their smaller telescope, Koch, Disney, and Taylor urgently needed a smaller diaphragm. They partnered with Bob McAllister to develop a diminished diaphragm for their telescope. Using tweezers, razor blades, and a microscope found on site, they fashioned a hole measuring 1/10 of a millimeter in aluminum foil from a TV dinner. Ultimately, at approximately 5 o'clock in the afternoon, they attained success. Koch and Disney inserted their small diaphragm into the telescope and began observations at dusk. This time, however, instead of monitoring a display, Taylor envisioned the concept of auditory observation of the photometer. When the telescope was accurately aligned with the pulsar, Taylor perceived the pulsations as a series of rapid clicks, akin to a playing card pressed against the spokes of a rotating bicycle wheel. Before 9 o'clock in the evening, Taylor perceived the distinctive clicking, signifying that the telescope was aimed at the pulsar. Nonetheless, Linz contended that they arrived tardily. While observing, the phone rang at the apex of the 0.9-meter telescope. Taylor answered the phone and conversed with Beverly Linz, the spouse of Roger Linz, an astronomer and the assistant director of the observatory. Beverly remarked, "You may discontinue your attempts to identify the pulsar, as Roger has identified it as the south preceding star." Marin and Linz employed the larger telescope to distinguish between the two stars. By concentrating on a solitary star and completely blocking the illumination from others, they promptly discerned the star accountable for the optical pulsations, Bade's star. The discovery that the Crab pulsar emits visible light is noteworthy for several reasons. The focus is primarily on energy output. A large radio telescope detected the Crab's radio pulses, while a smaller optical telescope recorded the visible light pulses. This signifies that visible light emits significantly more energy than radio waves. The visibility of the Crab Nebula 900 years after the event remained ambiguous. Jerry Fishman said it is akin to hearing a firecracker the day following its explosion. The pulsar continuously provides energy to the nebula. The Crab pulsar has become one of the most important pulsars studied and is anticipated to retain this prominence. Pulsar astronomy was set to develop into a separate scientific discipline from this point forward. Both observational and theoretical research thrived after the significant discoveries of 1967-68. This book analyzes the significant advancement of pulsar astronomy and its impact on diverse astronomical endeavors, such as identifying the first exoplanets and confirming general relativity. On Saturday, January 18th, Willstrop was informed about the detection of optical pulses from the Crab Nebula. It was only at that moment that Willstrop felt assured regarding the likelihood of achieving significant progress in his pursuit of optical pulses. Despite having observed the Crab, he concentrated on locating white dwarfs, among the most promising candidates for pulsars. Willstrop told me, "I had accumulated a substantial data set on white dwarf stars. Hewish et al. Posited that the pulsations of white dwarf stars were the origin of the radio pulses initially observed from CP 1919, among others, and one of my aims was to ascertain whether white dwarf stars displayed rapid optical pulsations. Moreover, substantial uncertainties existed concerning the quality of the Crab observations. The precision of the radio position may vary by up to 10 arc minutes, potentially placing it beyond the Crab Nebula. Furthermore, despite utilizing a 1 mm diaphragm with his photometer, the field of view was restricted to 50 arc seconds, allowing significant interference from Cambridge's background skylight into the photometer, thus obscuring the pulsar signal. Due to the uncertainty regarding the pulsar's position, he was forced to examine an impractically extensive sky area for a possible non-existent. Thus, he aimed the telescope as close as possible to the center of the Crab Nebula. Bade's star was too faint to observe except on exceptionally clear nights, and engaged the photometer. In the face of these uncertainties and the lethargy of computational processes in 1968, Willstrup concentrated on the data collected from white dwarfs. On Sunday afternoon, he conducted an order of magnitude calculation, estimating that his November observation could reveal the flashes. As midnight neared, he observed the crab once more. The IAU circular formally declared the discovery by Koch, Disney, and Taylor, which reached Cambridge on January 24th. Willstrup reviewed the observations of the crab he had conducted 2 months earlier. The optical signals from the crab pulsar were consistently present. Had Willstrup initially examined the smaller data set from the crab, he would have recognized the first optical pulsar.